This is what's it officially called? Fundamentals of Chemistry. This is the one semester version of chemistry that's we sort of skate across the top of topics and dig into some of them occasionally, but you can't go too deep when you're trying to cover uh, the topic of chemistry in just 15 weeks. I mean, it's a tall order. And I'm assuming that your career choices, your program choices, only require a basic knowledge of chemistry. So let me find out where you're coming from. What programs are you in? I know last semester, everybody in the program was a MLT. Is that the case this time? Is everybody MLT? You're all muted. I hope you can hear me. Maybe I better check my sound.
Yes, mine is MLT.
Okay. Hannah's MLT. How about John? You MLT? This also lets me know that there's somebody there. I know Hannah's there because she responded. Is John there?
I'm in the Associates in Arts program.
Okay, okay.
Only
And
got it working.
okay. Sometimes what you can do is if you're muted, just press the space bar and it'll unmute you.
That's neat.
Okay. And Tiffany, you were in my class last semester, weren't you? Earth to Tiffany. All right. Well, that's enough of that. Let's get with the program. Oh, there's chat. Hold on a second. Let me check my chats. Okay. So, what I'm going to do today is do an introduction and dig into the Brightspace course, because everything that we do in face-to-face is duplicated in Brightspace, except for the hands-on parts where we have to go to the lab and do experiments. But all the documents, even I can give you permission to take your test in Brightspace if you have a valid reason, like you're stuck at home and you can't get away for some reason, maybe a sick relative or you're snowed in or whatever the case may be. But I have to authorize it individually because this is a face-to-face class and we're supposed to meet face-to-face, weather permitting. And just so that you know you're in the right place, I'm Dr. Bly. There's let's submit my tag. There we go. Let me twist it so it level. I'm adjunct. In other words, I'm full-time with New River Community and Technical College on the Raleigh County campus. And Southern contracts me to teach this course and the 2-semester version of chemistry. So this semester, every semester we offer 203 because it's just one semester course. But in the fall, we do 213, and in the spring, I do 214. So, and Fridays are the only days that I can get down there. And I do all that, both those courses on Fridays. So if you're wondering why everybody else has their courses on Monday through Thursday and you have to come in on Friday, is because your instructor can't be there any other day. Okay, as far as introduction goes, I'm going to assume that everybody is familiar with how to get to your Brightspace course, because that's the place I'm going to start. And to do that, I need to share my browser. Let's see if I can find it. There it is. Okay. So this is where you would start once you get to your course. If you get to the Brightspace homepage and you need to find your course, you can do it two ways. You can either scroll down to your course, or you can hit this waffle. And I assume everybody's familiar with the mini bar. That's what this thing is called. There are several useful tabs in here. We're gonna come back to content because that's where you go to the meat of the course. But you can also access assignments through this location here. And before I go any further, I think I better tell the system that I'm a student so it won't show you a bunch of stuff you don't need to see. Come on. There we go. Now it thinks I'm a student. All right. So let's see. Christopher just showed up. Christopher Gargan. Okay. That's 1, 2, 3. So we got 4 students out of 7. We might get lucky and have everybody eventually. Okay, so when you enter Brightspace, there are several of these tabs that are useful. First one I'll point out is the class list. If you don't know about the class list, it's got everybody in your class listed, plus your instructor. And if you want to email anybody, you just, if you want to do a broadcast like I do sometimes, you just click that, it highlights everybody, and then you can email the whole class. Or you can pick out one of these persons in here, say you want to contact your lab partner. Then you just click on theirs and email them. And you can't receive emails through here. You have to go to your email client to do that. But this is convenient for contacting members of the class without having to search through the directory. Let's see. Okay. And then if you want to find out where your grades stand, this is a good place to go. Right? And it lists all the grades that will eventually be populated one at a time. I will point out this first one right here, current course average. There is an item where, and I don't see it in here, so that's good news. Because Brightspace will calculate a course average for you, but it's not accurate because it doesn't include, it is incompetent to include all the variables that I put into the grading scheme. So I have your grades that I insert into my Excel spreadsheet, and I can be more flexible and manipulate them, get an average, and then I go to current course average that I created, and I put that grade in myself. So if you see a grade here, then the only grades that enter into that average are listed below. If you turned an assignment in, or you did a test and the value is not listed here yet, that means it didn't go into your average yet. So if you calculate an average on your own, which you can do, and it comes out different than the course average, that's probably why, because I haven't input an assignment or graded an assignment that you've turned in. Okay, let's see. Virtual classroom, that should be Zoom. Yeah, that's going to be Zoom. I don't think I have any listed here. That's the wrong place to go for Zoom. Let's see. Let's go into, we don't have any discussions in this class. Assignments, you can get to your assignments here. Right? Assignments do not include exams. Right? These will all be lab exercises and extra credits. I'll talk about the extra credits in a minute or two. Okay, so let's go to content. All right. And if it comes up looking strange, like this is the last page I visited, so it's going to show that. What you want to do is you want to start fresh, then you click on table of contents. And some of the things show up here, but really all the assignments are going to show up here. Start here, lessons and resources. Here's your syllabus. All right, so there's a copy of your syllabus. If we were face-to-face, in fact, I've got a box here with hard copies of everything that I'm going to show you. So if you want to just look at it in your PDF, your Acrobat Reader, then you can do that until we meet next time, and I'll have the hard copies for you. So I'll come back to the syllabus in just a second. This is my schedule. In other words, this is where I am every day of the weekday. So, for instance, on Mondays from this time to that time, I'm teaching these two classes, a lecture and a lab. And then on Tuesday I'm there, and Thursday I'm there. I have office hours. And you should be able to contact me through Zoom during any of these times. If I'm not there, then I've been called away to do something else. And I apologize for that, but sometimes administration doesn't give me a choice. But these are my intended office hours. I have one that's late, so you can get to me in the evening on Mondays. And then I have one early on Wednesday, and then one kind of middle afternoon on Thursday. And of course, I'm there all day on Friday. So if I'm not tied up doing something with another class, then you can contact me there, or you can come back after this class is over and I'll stick around and we can discuss your problem. But the way to get to the Zoom office hours is through, the link is listed in that schedule, but I also have a link here just to be convenient. Right. So you can click on that, and then you can open a meeting with me. Now, also, if you need to meet me during some other time that I'm not occupied, then we can set up a special meeting. And as long as I know that you're going to come in using that link, then I'll be there at those times. All right, let me go back. No, come on. Let's kill that one and go back here. Notice these breadcrumbs at the top. That sometimes they're there and sometimes they're not. But in this case, I can go back to this particular module. Now we can look at the syllabus. Okay. There's the electronic version of the syllabus. And both Southern and New River have adopted a standard format for their syllabi. My New River syllabi look a little bit different than that, but all of your Southern courses will look exactly like this, only they'll have different information depending on your course and your instructor. So this is how you can get in touch with me. My office phone on the New River campus is there. If you call that, you're probably going to get an answering machine. So just leave your message. It's automatically converted into an audio file and attached to an email and sent to me, so I can get your message pretty quick. If you want to contact me, if it's more urgent, you can text me on my cell phone. You can call me, but I may answer and I may not, depending on what I'm doing. But a text message is less intrusive and likely to get me. Of course, there's my email address, and these are our meeting times, right? This is the catalog description, right? This is the grading prerequisites and co-requisites. So I assume that you've at least had one of these to get into this course. There's your textbook. Now, we have the textbook. This Stoker book is hard copy. And you can buy used copies if you want, or if you have to buy through the bookstore because you're on financial aid, then you may have to buy through the bookstore. This lab manual is only offered through the bookstore. But the only reason I leave it on there so that you buy it, and it's going to be wrapped in cellophane, and don't open it. The only reason I want you to buy it is because I use some of those lab assignments in our course, and I modify them, and I just don't want somebody coming back and claiming I've infringed a copyright. So if you have copies of those and you're doing the lab, then all they can accuse me of is modifying their work. Because most of these labs are just bare bones. In other words, they don't do everything I want them to do, so I've modified them. But this is just to protect us from copyright infringement, partially anyway. All right, other things that you're going to need in the course. You need a calculator. You need a scientific calculator. And I put in the functions that you're going to need, but if you go to the store, say you go to Walmart, and you go to their office section and you find calculators, if it says scientific on the package, then it's got everything you need. All you need to do is check your budget for what you can afford, and then take that calculator and learn how to use it. If you don't already know how to use a calculator and you have one, then this is your opportunity. You can only use calculators during an exam. Can't use cell phones. Smartphones have built-in calculators, but they also have access to the internet. And cheating is much too great a temptation using a smartphone. So smartphones, cell phones are forbidden during exams. Now, if you want to use your cell phone calculator to do anything else, that's fine. But if it were me, I'd want to know how to use that calculator if I'm going to depend on it for an exam. I would learn to use it and keep it with me. Laboratory materials. You're going to need a lab coat, right? It needs to be knee length, and it can be any color you want. It can be any material you want. Most of my students buy their lab coats from the internet. Or if you're in another course, say you're in MLT or in some other lab course, and you already have a coat, great. That problem solved. We do have eye protection in the lab, but a lot of them are scratched, right? So the visibility through them is not very good. I have a few that are in pretty good shape. But if you want to guarantee protective eyewear, buy a pair yourself. Now, you can buy full goggles, or you can buy those wraparound polycarbonate covers that'll fit over your glasses even. They're big enough to do that. But they look like sunglasses, except they're not tinted. We will provide disposable gloves, right? And that's basically all you need for safety in the form of materials. All right, grading scheme. We have 4 exams, and they account for 70% of your grade. And then we have 10 laboratories, last count. We have 10 laboratories, and they will add up to 30% of your grade.
Also,
One of the problems of working from home. Telephone interruptions. Okay, so the grading scheme is a 10-point scale. Right? If your average is 90, at the end of the class, you got an A. And so forth. And most programs require that you pull a C or better to progress in the program. So you may pass with a D, but it may not be applicable to your program. It may only allow you to get into another course that has a prerequisite. All right, let's see. I'm going to skip this stuff because it's okay. Here we go. Right. Well, that just says we'll have regular exams. Makeup exams are difficult because I'm only there 1 day a week. So makeups, I usually authorize you to take a makeup exam on Brightspace. And I have to give you permission to access the exam. Now, when we get into the course, I'm going to show you places in the course. Once we get in there, you may see a module named exam for each one of the those 4 exams. But if you click on it, there won't be anything there because it recognizes you and says you don't have permission. Right? So I have to give you permission to make up an exam in Brightspace. Everybody knows how to be a good citizen in exam etiquette. Everybody knows how not to cheat, right? I never did cheat because I figured it was more work than it was worth. I mean, it was easier just to learn the material. So I never bothered to cheat. And I've had very few students that actually tried it. I can count on one hand how many in 8 years of teaching at the college level. So I know there's I don't want to hammer this too long, but there's a protocol in Southern that says how you deal with cheating, right? It's very bureaucratically driven, lots of paperwork. It bogs everybody down and just ruins the whole class. So my alternative is before I go to administration about a cheating problem, say, for example, you decide that you're going to cheat on an exam, right? And I either catch you red-handed or I have sufficient evidence to know that you did, right? The next exam you take from me is going to be special. I'll leave it at that. Let's see. I got a little blurb on artificial intelligence. I'm not saying that you can't use artificial intelligence like ChatGPT to compose paragraphs for, say, your lab report or something like that. But it's just a caution. Watch out for what the artificial intelligence tells you is true, because these tools have been known to just fabricate facts from thin air and put them together in their. In fact, I actually saw a report where psychologists had evaluated products from artificial intelligence, and they concluded that many times these artificial intelligence programs are psychotic. Right? They display all the symptoms of psychosis. So just be aware of that if you want to use it. All right, so here's the schedule. This schedule is also reproduced as a separate item in Brightspace, so that you don't have to go into your syllabus to find it. I'll show you where that is in a few minutes. All right, so there's a lot of information here. Besides the meeting times, I've got this link here. So what you would do is you would highlight it and then say right click and copy it, copy the link, and then go out to your browser and put it into the address line and initialize it, and that will bring you to the course, assuming that you're there at 8:50 on a Friday. If you are in a position where you can't get to class, and you also can't get to your computer, but you do have access to, say, a tablet or a smartphone, and you still want to zoom into the class, then you'll need the Zoom app loaded on your phone. Then when you call up the app, it's going to ask you for a meeting ID, and that's what this is right here. And then it's going to ask you for a passcode, and that's the passcode. So if you have those 2 numbers, then you can Zoom the class from your smartphone or a tablet, or you can do it from your from any computer. But if you can't open a browser and do this, then use the app. Okay, so I've highlighted important things here. All the exams are highlighted yellow. On this date, 9 February, we have exam 1 on chapter 1, 2, and 3. on March 8th, we have exam 4, 5, and 6. Chapters 4, 5, and 6, exam 2. Then April 12th is chapter 7 and 8. And May 3rd, which is the final exam week, this will be the last day of that week, we have our last exam. So what that means is there's no comprehensive final. And that's out of necessity because Southern has chosen, it's probably been maybe a year and a semester. Southern cut a whole week out of their schedule, right? A whole week of instruction is gone. Now, I'm sure they've managed to satisfy the Higher Learning Commission that they're actually giving you a full semester of instruction, but chopping that week out just completely wiped out a whole session. So I said, well, what has to go? Because I can't cut out the instruction. So I just chopped out the final exam. So there's no final. And you can thank administration for that one. All right, I will point out this one day that I have to be absent. I had no choice. New River has a mandatory meeting on this day, the 8th of March. So what I will have to do on that day, since there's an exam scheduled, I will authorize everybody in the class to take exam 2 on that date in Brightspace. Okay, and we'll go there in just a few minutes. And this is a reminder that I will be absent, no face-to-face class, there's no lab scheduled. So all you have to do on that day is take the exam. And this is just a caution, don't show up in person because I won't be there. Okay, other things I throw in here just as a reminder, March 4th is the date that I have to submit midterm grades. So that means everything before then will average into that grade. And then, of course, the final grades are on May 6th. All right. So as you look down through here, you see what we're going to do on each day. Right now, we're talking about class business and the syllabus and expectations. And as soon as we get through with that, I think I'll probably go to safety, and we'll cover safety first, and then I'll finish out chapter 1 and chapter 2 lectures. Let's see. Okay. So this tells you the lab number that we're going to do on that day, and that's safety, right? It's not a big deal, so we can do that without being in the lab. Next Friday, we're going to do a lab that's you wouldn't consider hands-on in the lab because we're going to work on graphing techniques. In other words, we're going to learn how to present your data, your results in a lab experiment in graphical form, because that's a very common way that scientists use to present their data and make a point and try to argue their position based on their experimental results. So we'll do that one in class. Lab 1, this tells you when this lab right here, this lab is due on this date. Okay, so when we come to class on the 26th of January, assuming it's not snowing again, you'll hand in this safety practices. So what you're going to have to do is print out a copy from Brightspace and complete it before you come to class. I'll show you where that is in just a minute. Okay, and then underneath there, that gives you the name of the lab that we're doing on that day. So lab 2 is introducing graphing techniques. And the pattern is the lab that we did previous to this meeting, right? We're in class for introducing graphing techniques. The previous lab is due on that day. So sometimes we'll actually skip a week, right? So lab 2 is due on this date because we have a lab that day. Lab 3 is due skip a week on this day because we have a lab that day. So sometimes you'll be able to skip a week. And in this case, I'm gone. Well, that's 2 weeks there because I'm gone this day and we don't have a lab on that day. What you'll also notice is that whenever we have an exam, there's no lab. There'll be a lab and we'll introduce new material. I mean, there'll be an exam and we'll introduce new material. And that means there's not enough time for a lab. So whenever we have a lab, there's no exam. That's a pattern that you'll see. So I'll introduce material as shown in this schedule, and then we'll have a whole day to do a review. We'll have a whole class, we'll have a class period plus a lab. And part of that class period will be a review for the exam that comes the following week. And there's a document that I give you, and I'll show you where it is, that you use to help you focus your attention on the types of problems and questions that will come up in the exam. And we'll use that document to review. So when I show it to you, and if we were in person, I'd give you a hard copy, work those problems as if it was an exam and find out where you're weak, and then focus on those areas. And if you just can't manage to get it, I've got another document that'll show you how I did it. And if you still don't get it, bring those problems to class and we'll iron out the problems. Maybe somebody else in class has figured it out and can explain it better than I can, but I will definitely, that's your opportunity to correct problems before the exam. Okay, so that's the layout of the course. Other things, attendance and participation, that's the administration puts that in there. Bonus and extra credit, I put that in there. I have 2 bonus exercises that are independent of any other lab or exams. One for, I think, is for this, for the material in exam 1, and the second one comes in the material for exam 2. But I'll show you where those are. But I would also add that if you find yourself in trouble later in the semester, I encourage you not to ask me for extra credit to make up the difference. Because if you're in bad shape toward the end of the semester, that means you don't know what you're doing. And no amount of extra credit is going to help you understand what you missed in the first part of the semester. So if I give you an extra credit exercise, then it's for your benefit to help you learn the material. Also, exams will usually have bonus questions in them. So you can try them or not. It won't affect your grade. It can only improve your grade. But it's all based upon material covered for that exam. So the point is, learn the material, right? Extra credit is not a way to go through life, right? Learn the material and master the skills that you're going to need through this course, and the grades will take care of themselves. All right, there's some tips for a successful low-stress experience. I'll let you read those on your own. You don't have to pay attention to the appendix unless you just like the topic, what do they call it? Assessment, right? Assessing the progress of the course and students. This is the matrix that we use. And I put it in there simply so that it doesn't get lost, right? Because I put a lot of work into this, and all I need is for somebody else to come in and teach the course after I'm gone, and it's not there, so they have to start all over again. All right. Appendix 2, you would want to pay attention to. This references my office hours, how to contact me through Zoom. And if you load that Zoom app on your phone, then you can connect through the meeting here. You can either connect through this link down here, or you can input the ID and the, actually, you only need the ID for Zoom office hours. I don't have a passcode for that. The only reason I put a passcode in for the class meetings is so that we don't get interrupted by somebody bombing our Zoom session. I've been in a Zoom session that got bombed, and it was not fun. Okay, so there's my personal schedule again, just repeated. Okay, so any questions about the syllabus? Unfortunately, there are far too many students that never read the syllabus. They only read the syllabus when they panic and they're saying, I missed an assignment. Why? Well, because you didn't read the assignment. I mean, the syllabus. Read the syllabus. It tells you everything you need to know. Now, some of you may have already learned that, right? You know, kudos. But if you're in the habit of just not reading the syllabus and expecting to intuitively pass the course, then you're probably going to be in for a rude awakening. Okay, so let's go back to, let's see, here. And there's the course schedule again. So you can find the course schedule here. It's under, yeah, it's under Start here. I'm going to reload it just to be sure. Yeah, okay. So when you click on Start here, the first thing you're going to see is the schedule. Right? So there's the schedule again, and you don't have to open your syllabus to find the schedule. Well, there it is. You can click on this one and get nothing but that. Here's where you would click on the Zoom meeting link. This, I don't give any homework in this class because I don't have access to an external homework website that will grade it for me. I don't have time to grade everybody's homework. There's just not enough hours in the day. So if you want to access this homework, it's in a PDF file. And by the way, if you don't have a PDF reader, right, an Acrobat reader installed on your computer, get one. Right? You can go to Adobe Acrobat website, download their free Acrobat reader, and you'll be fine because all of my documents are in PDF format. Right? So if you click on that, you have a list for each exam of your chapters, right? Chapter 1, Chapter 2, Chapter 3 in your textbook, and these are the problems at the end of the chapter. If you want to drill yourself even more than you do in the review document, then these are good problems to work. Okay, now let's see. They're not going to help you much unless I give you the answers too, right? All right, so if you choose to do that, then let me make myself a note. I need to put the key in there, the answer key. Because if you use that, you're going to need to know whether you got them right or wrong. Let's see. Answer key for homework. Okay. I'll fix that before too long. All right, now let's go back over here. And we're down to homework. Okay, so here are your module. Each module is all the material that we're going to cover for that exam. And then the lab exercises are in a separate module. We'll look at those in a minute. All of these modules are set up exactly the same way. This one, if you have not already had some exposure to chemistry in the past and had to learn the symbols, then this is your opportunity. I would hand this out in class, but here you can get it and you can go ahead and get started. This is a periodic table, and I've identified the elements and their symbols. Notice there are no element names here. You have to look them up. Take the symbols and look up the name for them, the element name. Should be able to find that in near the front cover of your textbook. Listed in alphabetical order. And I want you to memorize the element name and the symbol that goes with it for the ones that are highlighted, that are surrounded by red boxes. Okay. It's about 60 of them, about half. The rest of them you don't have to memorize unless you just want to. Okay, and you only have to memorize the symbol and its name, right? All this other information in here is going to be provided for you whenever you need it. But you need to memorize what the symbol represents, because when I provide you with a periodic table, say on an exam, it won't have the name of the element there. It'll just have the symbol. So how do you memorize these symbols? The best way, I think, is to buy a stack of 3x5 cards. And on one side of a card, write the symbol, on the other side, write the name. And you've already started memorizing them by doing that. Then when you get them done, take that stack and you see the symbol, name it, turn it over, got it right, put it in one stack. Do the next one, get it wrong, put it in that stack. And you keep going until everything, you keep going with the wrong stack until everything's in the right stack. And then you pick up the right stack, start all over again. And you keep going until you can name every one, either the symbol for the name or the name for the symbol, both ways. And everything goes into the got it right stack. Once you can do that, then you're going to start using them. And that'll also be a process of memorization and reinforcement. If you don't know the symbols, you can't do chemistry. That's just that simple. You got to know the vocabulary. Actually, the alphabet of chemistry are the chemical symbols. All right. So let me go back. Those are the ones you need to know. And I think we encounter the symbols in chapter 3. We actually start using them, talk about the periodic table. But memorization takes time. I mean, when your mind is young, you can memorize quickly. When your mind is as old as mine, it takes a while. So I would start memorizing now and do it little at a time. Why? If you know anything about human physiology or in psychology, I don't know if any of you have taken anatomy and physiology, but if you have, you may have been introduced to the concept of short-term and long-term memory. Short-term memory is only good for, on average, storing about 15 to 20 minutes worth of input. So these classes are what? 8, 12, 4 hours long, right? You can't store all the information that I'm going to give you in 4 hours time in short-term memory. There's not enough room. So you got to start moving it into long-term memory. And that takes time and effort. So that's why I record everything that we do in class, because even at best, the notes that you take are only going to be about 50%, if you're lucky, of what's covered in class. So you go back and look at the video and see what you missed. All right, so know these. And then for each of the chapters, you can open them up. These are, excuse me, that's the wrong one. Click the name. There we go. So this is going to show you the PowerPoints that I would give you in class. They're in 3 different flavors. They're all the same thing, 3 different flavors. One is actually a PowerPoint presentation. So if you have Microsoft Office, you can download this set of slides and view them on your computer. Or you can look at this set of slides in your PDF reader. They just won't have all the animations and videos, if any are embedded. But if you go to this one, it calls up an HTML file in your browser, and you only need your browser to view it. Right, so if we call that up, let me see if it's working. Yeah. So there it is. And all you would have to do is click on it, right? Or click down here. And you can view all the entire set of PowerPoint slides in your browser. You don't have to open them up in any in PowerPoint or PDF. All right, let me go back. That was chapter 1. So chapter 2 and chapter 3 are exactly the same, only for different chapters, obviously. So let me go back over here and let's go back. Let's get everything up over here on this side. If it's too busy, just click on collapse all, and it shrinks things until you need them. What I'll do also, these are the videos from the fall semester, right? So if you want to go ahead and look at those, I cover the same material. It just won't be familiar to you because you weren't there when I did it. So what I do is when the recording is done, I will process it for appearance, for dead air. I'll cut out the dead air. Sometimes I'll even correct mistakes. If I misspoke during a lecture, I'll put a correction at the bottom. Then once I process the video into an MP4 file, I'll upload it to my YouTube channel, and then here I'll create a link to that video. So when I get the video for today finished, chapters 1, 2, and I'm not sure if lab 1, we'll talk about that. Then I'll replace this one with the current one, and I'll move this one into another folder where I keep all my archived videos. Right, so you can go back and look at anything. The further back you go, the worse the quality. Right? So I wouldn't waste my time on the really old ones. All right, so those is where the videos are going to be. So I'll have the videos for the lecture, have the video for the review. Here are these are Brightspace. This is a Brightspace quiz for chapters 1, 2, and 3. And it's a way for you to get familiar with the way the Brightspace quiz looks if you take it in Brightspace. So exam 2, you're going to be taking in Brightspace. So when we get to module 2, you may want to use this Brightspace review. And you don't have to, in order to do this review, you don't need lockdown browser. Only when you take an exam do you need lockdown browser. So you can do this over and over and over again. You can drill it until you can do it in your sleep. These guys are Word documents. So these are actually, these are compiled into a single document that I hand out in class. All right, so these are separate documents, but they all together, they are compiled. I hand out those in class. I'm pretty sure that's the case. Yeah. Okay, so it's multiple choice, right? Okay, so you can look at these, and when we get to class next time we see each other, what I'll do is give you a hard copy. It's got all these together. They're separated here, I think, because that's the way I created them. Okay, let's go back and see what else there is. Okay, let me go here. Now, down to exam 1. So it knows I'm a student, and it knows that I don't have permission as a student to take the exam. So all there is here are the instructions. There's no connection to the exam here. Right? I would have to go back up here and become the instructor. Then I can show you that one. And I'll do that just to give you an idea. Let's go down and look at module 2, because that's the one you're actually going to be taking. Oh, we got another one show up. Mr. Alexis. What's Alexis doing here? Oh, there we go. I see. Sorry. I found you. Zoom. Okay. So we're only missing 2. Okay. So if it knows I have permission, then you come down and you open up the exam, and there's the link for the exam. So if I click on that link, it'll take me to a page. No, it knows I'm the instructor, so it's not going to shoot. What I was wanting to show you was at the bottom of the page, it'll say begin exam or start exam. But right above that, it'll have a link to install Lockdown Browser. If you don't have Lockdown Browser on your computer from, say, another course, or if it's been several months since you used it, you may have to update it. You'll click on that link, and it will install or update Lockdown Browser and Respondus Monitor. And then you can go in and take the exam. Now, I'm not sure. Let me check myself. Well, let me go back to I don't see it there. All right, I didn't include one in this course. I have put a practice exam in there before just so you can check out your equipment. But the exam, when you take exam 2 in Brightspace, it's going to tell you you have so many minutes to complete the exam. Don't panic. Those are the minutes that I think you should need to complete the exam. But if you go run past that number of minutes, it will not kick you out. It will not automatically submit. So you can just keep going till you're finished. All it does is it tells me that this student or that student needed more time. They ran over. Or some students finished early, some students finished late, and it gives me a better idea what to do next time I offer that exam to adjust the time. So don't panic. Just keep working until you're finished and submit. Now, if you lose your internet connection or you lose power during the exam, I'm pretty sure that your answers, you tell it to submit each answer before you submit the whole exam. You submit each answer, so it stores your answers. And you should be able to contact me, and I can reset the exam, and you should be able to go back into the exam and pick up where you left off. All right, so I'm going to go back and be a student again. Here we go. Okay, let's see, where was I? We're talking about, let's see, PowerPoints, reviews, exams, extra credit. This is the first extra credit independent assignment, right? So what you do is you go in and you click on this. Like I said, if we're meeting face-to-face, I give you a hard copy. But you're going to have to print this out if you want to get started on it now. If you want to wait till our next meeting, that's okay, because it's not due until the date of the first exam. But I'll show you what it looks like. Here's the document, right? You have the document there. You need to download the document. Let's see. I got my download covered up, I think. Yeah, it's over here. So you download the document, store it someplace. Then you go open it in your PDF reader, and it's got this page of instructions. Don't forget to put your name up there. You're going to print it out. So write your name up there, and then go to the second page, and there's your blank periodic table. The instructions tell you how to fill it in. All right. So you want things like number the groups, right? And that won't mean anything until we talk about the periodic table. Number the periods, heavy black line dividing the metals and non-metals, things like that. This tells you everything to do, and sometimes what color to use also. So I would suggest using colored pencils. They're more, they produce a finer line, and in that little page, you're going to need to write small to get everything in. And then when you finish it, right, you'll turn it in, and I'll use this page. So turn it in with this page. I use this to grade, and I'll grade it by these points with a possible total of 407 points. That would be 100% for this extra credit. Okay, so if you bring it to class and hand it in, that's great. If you forget and you come to class on the exam day and you don't have it with you, you can go back in here and say upload. And upload, go find the document, submit it, and I'll get it there, right, before the deadline. The deadline will be midnight on the day of the exam. All right. So that's the extra credit assignment for exam 1. There's another extra credit assignment for exam 2. We'll get to that later. Now, what are the extra credits worth? This extra credit and the second one together are worth 1/2 of an exam, right? Those points are added in on top of whatever you've gotten. They're worth 1/2 an exam. So their value is substantial. Plus, if you do the exercise, it's going to help you learn how the periodic table is structured and help you learn the symbols. So I would encourage you to take advantage of that. Okay, that's exam 1. All the other modules are set up the same way. PowerPoints, videos, review videos, archived, exam, and let's see. Actually, sometimes if I think it's instructive, I'll record a discussion of the lab, right? When we talk about the lab before you actually do it, then sometimes I'll incorporate that. It's not regular, right? Only if I think it's of value. But in this case, we have one that's listed there from a previous semester, so that would be valuable for when you get to this particular lab, binary mixtures. All right, so let's look at the labs next. These are all the labs. I'm going to collapse it for now, right? And numbered the same way that they are in the schedule, right? 1 through 10. So if you miss class, you don't get your hard copy, you need to bring the hard copy to class. And sometimes these exercises have pre-lab questions. Those pre-lab questions are supposed to be answered before you get to class and go into the lab. Right. Let's see if I can find an example. So lab number 3, let's look at that one. So here you have lab number 3. There's the document, the assignment, and the document is right here. Okay, so you'll want to download it, and each one of them shows you how many points. And by the way, this class, the lab exercises in this class, the reports that you submit are, you fill in the hard copy. In other words, you answer the questions on the hard copy. So we have to get down to where there's some place to write. All right, we go down, lots of that introductory material and instructions. And then we get to pre-lab questions. You answer those before you get to class. And you just write your answers in here. Okay? And the points that are assigned to each one. There are no formal reports in this class. There's just, I mean, that's probably going too far for an introductory class. So you'd have to take the 2-semester version to learn how to create a formal report. So your reports are based upon these answer sheets. All right. So let's see. I thought I had this one set up so that you could fill it out. I guess you're gonna have to do it by hand. All right. So if you're gonna, if you bring your hard copy to class, you gather your data during the experiment, you write it down, and then after the experiment, you take it home and you finish doing the calculations and answering questions. So you have two choices. You bring it to class when it's due or before and hand it in. End of topic. If you miss bringing it, you can submit it here. But since you did it, since you completed the report by hand, you can only submit an electronic copy here. So you've either got to scan it or take pictures of the pages and upload them here. If you take pictures and you can produce a PDF file from those images, that's great. That makes my work a lot easier. But if you can't and you have to submit individual images, then I will compile them into a single document and grade them. If you submit in Brightspace, I won't hand you back a hard copy. I will simply annotate while grading, annotate your submission, put a grade on it, and upload it along with your grade. So when you see your grade at this location, there should be a link to access the my return. All right, lab exercises. So there are all the 10 lab exercises. This is the one that we're going to look at today. I'll come back to that, but you get it the same way. Also, there are often video links from the past on each one of these labs, right? So there's an introduction. Okay, right. So apparently I have introductions for many of them. This one, laboratory techniques, where we actually go into the lab and learn how to use pieces of equipment. This is a demonstration laboratory technique. That's where I go into the lab. I did these back when COVID was marching across the country, and created these demonstration laboratories because we couldn't meet face to face. So my class, we would meet by Zoom, and my class their assignment would be to take the exercise document and view the demonstration that I did for them in this video and gather the information, the observations and data from the demonstration and fill out their report and submit it. So I don't want you to take the data from the demo and put it in your report, right? I'll know if you do that. But this is a good way to view in advance what the exercise is going to look like when you go into the lab. So you're welcome to view it. You just don't take any of the observations or the data from it. Do that yourself in the lab. And let's see. Yeah, there's another one. Sometimes I have added information like this PDF file on the density of metals. This stuff that you would get hard copy in the lab if we were face to face. And let's see, I'm just looking for anomalies. There's several links here. There's my demo. Chemical change, there's another demo. I think I got demos for all of them in here. No, I don't have a demo for this one. That's odd. There's another demo. So I missed Boyle's law doing demo. There's another demo. And this one is a demo. So Boyle's law is the one I missed putting a demo in there. I'm not sure what happened there. There's an introduction. There's a discussion. I have to look into that. Okay. Stop me at any time if you have questions. If it's all making sense to you, then great. All right. Let's see. Did I miss it? I don't think I missed anything in Brightspace. So what I want to do next is discuss the safety lab. So why don't I call it up here since it's available? Here. Let's see the document. Here we go. There we go. So this is the document I would hand out in class. It has a discussion of safety precautions in the lab. Right? If you can't conduct your lab exercise safely, then you shouldn't be there. Right? And I was a federal government employee for 22 years. And my job was to do research, agricultural research. And that involved lots of things. I was out in the field, I was in the greenhouse, we used growth chambers, and I was in the laboratory conducting analyses and experiments. And the overarching goal of the government was to allow their employees to conduct themselves through an entire career of 20 or more years without any adverse effects on their health or quality of life. And they went to great pains to instruct us on safe practices. And we had periodic in-service trainings to do that. We learned, we got CPR training. We learned how to combat fires. We learned how to clean up hazardous materials. We learned how to conduct ourselves in the laboratory and the field environment too, safely, right? Protective equipment, what types of materials need to be treated especially carefully, like insecticides, various pesticides can be, over a long term, can be lethal. So safety was a big concern, and the one rule that should override everything is before you conduct an experiment, before you do anything in a scientific investigation, is know what you're going to do before you go in and do it. Information and familiarity with the experiment beforehand will keep you safe. That's why I give you these laboratory exercises at least a week in advance, so that when you come into the lab, you have read them, you have digested the procedures, and you have a better understanding of where the safety traps are in that lab. Okay. Things like how do you detect odors safely? How do you work with glass tubing? We're not going to do that, but this is an example. Other things like protective PPEs, personal protective equipment. I'll show you in the lab where the material safety data sheets are. They tell you everything you need to know about any of the chemicals we're going to use and what the safety hazards are. Like acetone, it's a fire hazard, right? It also has a health hazard. It's an irritant, and you don't want to inhale it or get much of it on your skin. You can get some of it on your skin, right? And anybody who uses nail polish knows what acetone is, and you know what it smells like. Use it to remove your nail polish, right? But only minor exposure is safe. It's the long-term exposure and the flammability hazard that is the problem. That's just an example. Okay, so what do you do? You also have to think in advance. What do you do in an emergency situation, right? Say somebody gets too close to a Bunsen burner and their clothes catch on fire or their hair catches on fire, right? Every grade schooler is taught this one: stop, drop, and roll, right? Okay. Well, in the laboratory setting, we add a layer of safety to that. We have what we call fire blankets, and I'll show you where they are when we get to the lab. They're hanging on the wall, and there's they're in an enclosure, and there's a rope handle sticking out of the enclosure. You just go grab that rope and you start turning, and the blanket feeds out of that thing and covers you, and then you can drop and roll. If you cut yourself or you get burned, how do you treat those wounds, right? If you get cut and you're bleeding, right, first thing you do is direct pressure, right? Some type of compress material, a handkerchief or a wad of paper towels, and direct pressure, right? You don't use a tourniquet unless you absolutely have to. And then somebody has to go call 911. I don't know if any of you have been trained in CPR, but it's a good skill to have and to renew from time to time. What happens if you get experience a chemical spill? Right, say you drop a container and it breaks and it shatters and sprays you with some chemical. Well, we have a shower. If it just gets in your eyes, right, that's what your goggles are for. If it just gets in your eyes, then we have an eye wash station, and you bury your head in that eye wash station, pull the handle, and drench your eyes for 20 minutes. Right? You blink your eyes and you rinse them for 20 minutes. You can be sure that chemical is out of your eyes, because that's one thing you don't want to lose is eyesight. If you get it all over your body, that's what your lab coat is for, right? If it lands on your lab coat, you can strip that off. And after you strip it off, if you still got places on your body that are irritated and you can identify that you've been spattered, you go to the shower, stand in the shower, yank the handle, and by the way, don't yank that handle unless you intend to be drenched, right? If you need it, fine, it's there for you. But don't pull it unless you need it, because gallons per second will come out of that shower, and the whole lab will be flooded. There's a drain for sure, but it's not big enough to drain that much water fast enough. So when you do that, if you need it, by all means use it. But the whole lab will be flooded, and of course we'll probably suspend activities for that day. But your health is more important than that. We have fire extinguishers in the lab. I'll show you where those are. And they're what's known as ABC. They're rated for any kind of fire, paper fires, chemical fires, fuel fires like flammable materials other than paper. They will smother any of those fires. Okay, so that's how you be safe. Now, safety information is, this information is for you, so that you'll know where the shower is. So you put in here, where is the shower? Well, in our lab, it's on the northwest wall, or the west wall, I should say. Fire exits, we have two of them. One's in the northwest corner, one's in the southwest corner. Eye wash fountain, we know it's in the northwest corner. Fire extinguishers against the northwest wall, west wall. The shower was in the northwest corner. That was my mistake. First aid station, there's also a first aid station located near the shower. Fire blanket is near the fire extinguisher, right on the west wall. Material safety data sheets are in a bound three-ring binder on the lab bench against the east wall. I'll show you where that is. Where's the nearest telephone? Well, it's in the southeast wall in the corner. But everybody has a cell phone, so that's only useful if, actually it's, no, telephone's not there anymore. Telephone is on the instructor's desk at the front of the class. Emergency numbers. I'll have to give you those later in class. Any additional safety instructions, you can put those in at your leisure, right? This is not graded. This is for your benefit to have that information. This is the safety agreement. I get a copy of this, and there's a duplicate. Actually, is there a duplicate? No, there's not a duplicate. So I get this copy right here, where you sign, put the course you're in, your locker number. We have to assign, actually they're drawers. We'll assign a bucket number once we decide who's who. So you can leave that one blank for now. I'll sign it and date it. You sign it and date it. What laboratory section you're in, there's only one laboratory section. So you just put a 1 there. And the room number, right? A234. Building A, room 234. I'm pretty sure that's right. Let's see. I don't want to tell you wrong. Yeah, A234. And you'll hand that in. And you can hand it in along with the safety quiz. So here you put in your name. If you've been assigned a group, fine. If you haven't, we'll do that later and date it. And then this is set up, excuse me, this is set up so that you can fill it like a form. Right? It's a PDF form file. And just answer these questions. Most of them are based upon discussions in this part of the document. Right? So, in fact, I'm not sure. I think this came out of your lab exercise book. I can't swear to that. I think it did, but maybe not. Okay, so you answer these, and when you turn them in, I'll grade them. They're a total of 21 points possible. And that'll be your first lab grade. Most people do fairly well. This is one where you can mess up. This is a scenario. Sarah walked into the laboratory and began reading the day's experiment for the first time. That's her first mistake. You read that experiment, you know what you're going to do before you even get to the door. All right. So you pick out the errors. And based upon the points, I think there are probably 9 of them that I'm looking for. So that tells you you're looking for 9 errors. So you fill those in there. Okay. Like I said before, any questions? You'll have to print this document out if you want to do anything ahead of time. There should be time in class. Since there are no pre-lab questions, you don't have to complete anything ahead of time. But I think you should print a copy and finish this before you come to class. Let's make that the rule. Print a copy of this one, download it. Actually, you don't necessarily have to print a copy, because if you load it up in your PDF reader, you should be able to complete it and save it. If you have Adobe Acrobat Reader, the newest version will allow you to save the form after you put your answers in, right? Before you close it, you may want to print a copy just to be safe, and then try to save it in your reader. If you can save it in your reader, great. Then you can print it out with the answers already there. And if the answers are typed in, then that makes my job a whole lot easier. So I don't have to figure out your handwriting. Okay, so let's see. That takes care of safety, syllabus, bright space. Now we can move on to, I'm going to stop this share. We're gonna cast a wide net in the beginning for most of the sciences. And then we're gradually going to narrow our focus to chemistry. Although chemistry is a pretty big umbrella in its own right. So here are the topics. I just put these in so you'll know the outline ahead of time, but I'm not going to stop here and talk about them. So, so that we keep our focus on chemistry and not go too far afield, like into physics or biology or some other fields of investigation. Chemistry is the study of substances, right? Let's make it really broad. Chemistry is the study of substances, their characteristics, how they're composed, and how they change from one substance to another. And key to that change is what I call identity. You can identify the material as unique. The substance is unique. It's not like anything else. It may have similarities with other substances, but no other substance is exactly like this one, right? There's no other substance that's exactly like water. Water is special, right? As well as all substances are. How they change. Now, sometimes they change their identity, and that would be a chemical change. Sometimes they change some characteristics, but they happen to be a mixture of different substances that do not change their identity. So the mixture takes on new characteristics, but they're not due to a change in identity of any of the individual components of that mixture. Okay. I was starting to get down too far into the weeds there, so I better stop and wait. We'll talk about mixtures later. Okay. So in order to study stuff, we need to understand what it is. Well, the broadest definition of anything in the universe is matter, right? Anything that has mass and occupies space is known as matter. And mass is a measure of the amount of substance. We normally equate mass with weight, but they're not the same. And I'll hammer that point in a few minutes. But mass is an expression of the amount of matter. So with that definition, no matter where you are in the universe, the mass of that object or that substance, the sample, is the same. Right? As long as you're not close to a black hole or traveling close to the speed of light, which we call relativistic mass, rest mass will always be the same everywhere. Now, matter includes everything. It can be living, it can be non-living. Right? So my PhD is in soil science. So I'm intimately familiar with the nature, the structure, the characteristics of soils. And on top of that, I have a little experience with plants too, agricultural crops. I study a little bit about rocks, not so much as a geologist would. And there are other substances that could be living. They could be naturally occurring. They could be man-made, right? A large portion, too large a portion of the substances we find on our planet now are man-made, and they're very persistent. Plastics is a good example. Right? We find places in the open ocean where the currents have concentrated flotsam. We call it flotsam, floating stuff. And much of that is plastic. So once we use plastics, they don't degrade rapidly. And they're persistent and a constant headache for environmental efforts. Now, as opposed to matter, there's also energy. So the whole universe is made up either of matter or energy. And in fact, we've learned that they're interchangeable, right? Einstein proved that with his equation, his famous equation. right? E equals mc squared. So we now know that energy and matter, mass, are equivalent using this formula. But we can study them separately. We don't have to study them as interchangeables. We can study energy as either heat or light or electricity, right? We're all depending on electricity right now, most of us, unless you have propane or natural gas heating your home. To stay warm, I use electricity. And these are not matter. These are energy. There are other forms of energy, but those are examples. Okay, so which of the statements best describes matter? Well, obviously, anything that has mass and occupies space. Okay, we can classify matter into different phases based upon physical characteristics. Right? So we can characterize a substance, a bit of matter, based upon its volume. How much space does it occupy? Right? And maybe its shape also. Right? Does it have a shape? Well, if it has a definite shape that it can maintain on its own without any outside interference, and it has a definite volume, both of those definite, it's a solid. If it has a definite volume, but it can't hold its own shape, then it's a liquid. It must be in a container. If it cannot hold its own shape, it needs a container, but it doesn't have a definite volume either. It's a gas. So gases are contained in a three-dimensional structure that has no exits. And the gas will expand to fill that space. Right? So these slides, I already gave you this information, so I'm just going to move on through. Examples, right? There's an Eisenhower Liberty $50, I think. It's a solid, right? There's a liquid. I'm not sure what that liquid is. It could be a copper solution, maybe, aqueous solution. But it needs a container. And here's a gas. It needs to be covered. That's probably, let's see, could be chlorine. Yeah, I think that's chlorine gas. And it has to have a cover on it. Otherwise, it would just continue to expand. Now, what factors contribute to the state of matter? And by the way, a substance, most substances, can transition between solid, liquid, and gas. They can change their states. Now, to be sure, their identity has not changed. If we're talking about a pure substance like water, for instance, if the water is a solid, we call it ice. If it's a liquid, we just call it water. And if it's a gas, we call it vapor or steam, right? So the things that determine, that influence the changes are first and foremost temperature, right? If we take ice and heat it, it will eventually become a liquid. And if we keep heating it, eventually it'll become a gas. Right? But for some phase changes, there is also an influence from surrounding pressure. Like water boils at 100 degrees Celsius at 1 atmosphere pressure, that is at sea level. But if you go to the top of Mount Everest and you start heating your water, it will boil at about 85 degrees, or maybe even less degrees Celsius. Right? So the boiling point is influenced by pressure. The phase change is influenced by pressure. And then there's this one topic that we will eventually say something about, is what is the force holding the particles together in your substance, right? Molecules of water, what holds them together? There's some attractive force that is holding those water molecules together. And it all depends upon the identity of the molecule or the element, the substance. What is its identity? What is its chemical characteristic? What is its structure? Will influence the strength of those forces. And the stronger the forces, the more energy you have to put into it to make it phase change upwards like this. So those are the three main influences on phase changes, the states of the matter, right? So the physical states we're interested in are solid, liquid, and gas. Now, to be sure, there are other states of matter, but they usually occur under very extreme conditions, like in the atmosphere of the sun, right? We have what's called a plasma, right? So, or if you go to a muffler shop and you want to have your muffler or your tailpipe replaced, the technician may grab a device called a plasma torch, a plasma cutter. And it is. It's argon gas that's electrified so high in voltage and current that the argon gas, we strip electrons away from it and produce an ion stream. And it's very effective at cutting through metal. And it's not as hazardous as a cutting torch. An oxygen acetylene torch, there's an inherent flammability and explosion hazard there. But with a plasma torch, it's relatively safe. Okay, so when we're trying to describe matter, we want to describe matter in terms of what are properties that characterize this matter that distinguishes it from other matters, from other substances. And those properties can be of two types. Think of it as the potential. What's the potential for a physical or chemical reactivity? Well, if the physical change is a potential, that is, if we know that water is going to boil at 100 degrees and go from liquid to gas, then if we say the boiling point of water at 1 atmosphere pressure is 100 degrees Celsius, that is a physical property because we're describing a potential for change. An example of a chemical property. Let's see. Let's go back to acetone. I have some nail polish remover, pure acetone, 100% acetone. All right. I'm going to tell you to be careful with it, not just because the vapors are toxic, but because if you get an open flame close to it in an oxygen atmosphere, it will ignite, right? It will burn. So the characteristic of the property of acetone, that it is flammable, speaks to a potential that is a chemical property. Okay, it has the potential to burn. We're not saying it's burning. We're saying it has the potential to burn. That is a property that is chemical in nature. All right. So there's a definition, and here are some possible physical properties. If you just observe a color of something, if I say the sky is blue, I'm expressing more than likely a physical property. Or if I walk down my hall and I smell a bad odor when I pass the laundry room, and a bad odor of a certain type, then I know it's time to go in and scoop out the cat litter. That's an odor. It's a physical property of whatever is in that room. We've mentioned physical state. If we say it's a solid, liquid, or gas, that's a physical property. Melting points, boiling points, hardness. If we say something is harder than something else, we're describing it in terms of a physical property. So if I say on the Mohs scale, diamond is a number 10. It's the hardest naturally occurring substance on Earth. Then I'm describing hardness as a physical property. Okay, so why is the boiling point considered a physical property when a gas's appearance is much different from that of a liquid? The appearance may be different, but we have not changed the identity of the substance. It's still water. And how do we prove it? We'll just take the gas and cool it down, and it'll condense into liquid water, same as as when it started. Chemical properties, as I described before, describe the potential for undergoing a change of identity, forming a new substance that is completely different at the atomic level, the molecular level, say, than the substance before. So, if we say that copper objects turn green in the air, and they do, right? If you've ever seen a building that's newly covered with copper roofing, copper shingles, copper sheeting, whatever the case may be, it looks very bright. In fact, it's a unique color. We call it a copper color, but it's very shiny. Well, after a few months exposure in the atmosphere, it starts to get dull. And eventually it forms this green color. They call it the patina, the green patina of weathered copper. And there's some buildings in Europe that are hundreds of years old and still have their original copper roofing. And it's beautiful color, right? Time adds to its appeal. We're describing a chemical property. It has the potential to change, right? Decomposition of something, right? If we say, I eat food and my body digests it, decomposes it into other substances in order for my body to gain energy and building materials, then I'm describing a decomposition of food, which is a chemical property of that food. It can be decomposed. Okay, which one of these is false? Well, let's see. Properties of matter are of two types, physical and chemical. That's true. So we're looking for the false one. So that one's true. We'll throw it out. It's not false. A physical property is a characteristic of matter that can be observed without changing its basic identity. Yes, that's a physical property. Chemical property describes the way matter undergoes or resists changes to form a new substance. That's true also. One example of a physical property of water is that it can be broken down into hydrogen and oxygen gases. That's false. The potential for decomposition of water is a chemical property because you're creating two new substances out of one original. You're creating two gases out of one liquid. Right, so this one is false. There's that copper patina on the Statue of Liberty. So let's see if we can classify each one of these as a chemical or physical property. Iron metal rusts in atmosphere of moist air. Right? You can answer it if you want. I mean, you don't have to listen to me talk all day. That's a chemical property, right? Mercury metal is a liquid at room temperature. That's a physical property. It's still mercury. And we haven't even tried to change it. It just happens to be a liquid at room temperature. In fact, it's the only metal that is a liquid at room temperature. There's one other non-metal that's a liquid at room temperature, and that's bromine. I just gave you the answer to two on that special, on that extra credit where you fill in your periodic table. One of the questions is, what are the two substances that are liquids at room temperature? So I just gave them to you. Nickel metal dissolves in acid to produce a light green solution. Okay, what's happening there is that when nickel dissolves in the acid, it's actually taking the metal and converting it and forming a compound with parts of the acid. And it changes its color as a product of that. Now, the color itself is a physical property, but the potential for nickel to dissolve in acid speaks to the chemical property that occurs. Okay. Now, we were describing properties first. Now we're talking about change. So what is it that's different than property and change? Property speaks to potential, and change describes the actual behavior, whether it's physical or chemical. So it's the process that occurs. Boiling or freezing water is a physical change. We're boiling, the water is changing from liquid to gas. Freezing water is changing from liquid to solid. We have described a physical change. By the same token, the process that describes the realization of a described property that changes the identity of the substance is a chemical change. Rusting of, say, iron rusts when it's left exposed to air, and it produces a new substance. Like iron becomes rust. We are describing a chemical change. We didn't say it had the potential to rust. Right? Say we paint it, right? It won't rust, but the potential is still there. That's a property. If we scratch it and expose the underlying metal to the atmosphere and moisture, then we're saying it is now rusting. That's a chemical change. So if you like flow charts to organize your thoughts, here's one. Physical property versus physical change, and chemical properties versus chemical change. Okay, which of the following examples is a chemical change? Well, if we pulverize rock salt, it's still salt, isn't it? Yeah, and we take it and throw it out on our roads in the winter. So that's not a chemical change. If wood burns, yes, we change the components of wood into carbon dioxide, water, and ash. So that is a chemical change. If we dissolve sugar in water, that's a physical change. All we're doing is putting water into solution. How do we know that the substances did not change their identity? All we have to do is separate them. Like boil off the water, steam, condense it, we got our water back. Boil off all the water, sugar's left in the bottom, right? So that is a physical change. And melting a popsicle is a similar idea. All you're doing is changing the state, changing the phase from a solid to a liquid. Okay. Now, in order to talk about mixtures, and one of our labs, let's see, lab number 4, we're going to investigate mixtures by separating a mixture of, let's see, we have table salt and sand mixed together, and we're going to separate them and determine what percentage of each was in the original. So this describes what a mixture is. Well, before you can have a mixture, you've got to identify what a pure substance is. Right? A pure substance is anything that has a single identity, and it cannot be separated into other substances of different identities by physical means. Right? If we mix sand in water, then we don't have pure substance. That's a mixture. But if we wait long enough, then the sand will settle out. We can decant off the water, and then we can dry the sand, and now we have them separated. Well, the sand is a pure substance. The water is a pure substance. And we separated them by physical means. We didn't have to apply any chemistry at all. So the mixture then is a combination of 2 or more pure substances. All right, and there are numerous examples. And in a mixture, one identifiable characteristic of a mixture is that all the components of the mixture retain their chemical identity. They are not changed chemically at all. They can be retrieved by physical means. So I did sand and water. Salt water can be the same way. All you have to do is evaporate the water, and you're left with the salt. Now, we can classify mixtures 2 ways. There is the type of mixture that has visibly different phases in its mixture. One example would be a jar of jelly beans, right? You know by looking at a jar of jelly beans that you have concentrations of color here and there, right? So it's not uniform throughout. You can't take a sample here and expect to get representative colors of every color that's in the jar. You might get a handful that's predominantly reds, or predominantly blacks, or predominantly whites. That's a heterogeneous mixture, right? It's not uniform throughout. On the other hand, homogeneous mixtures are uniform. In other words, it doesn't matter how much substance you have. Once the mixture is made, you can sample it anywhere, and you will have the same percentage composition of each of the pure substances in that sample. So if you mix your sample up to be, I don't know, 10% table sugar, and once it's all dissolved, you can take a sample here, analyze it, and it's 10% sugar. You can take a sample there, analyze it, it's 10% sugar. And homogeneous mixtures also go by another name called a solution. So chemically speaking, I mean, in the chemistry and physics of matter, you can have solutions of gases. You can have solutions of liquids. You can have liquids and solids. You can have solutions of solids and solids, as long as they are homogeneous. All right. So here's another flow chart. And these, I'm pretty sure these are derived from your textbook, so you should be able to find these in your textbook also. So which of the following is a homogeneous mixture? This brings up the a teaching point of how to solve problems. Sometimes problems are solved best by working backwards forwards. Go to the end and work backwards. So we're looking for a homogeneous mixture. Well, if any one of these is not a mixture, it can't be homogeneous because it's pure. So if we throw out the ones that are pure, then what's left is a mixture, and then we can decide whether they're homogeneous or not. So pure water is not a mixture. Throw it out. Copper metal is not a mixture. Throw it out. Gasoline, yeah, gasoline's a mixture. Jelly beans, they're mixtures. Soil, take my word for it, soil is a mixture. So now we have to decide which one is homogeneous. Well, I'll go to the one that I know best, soil. Soil is heterogeneous. In other words, if you see a roadside cut through a soil profile, you will see layers, right? So that soil is not homogeneous in color, in texture, in chemistry. How about a jar of jelly beans? Well, we've already described that as a heterogeneous mixture, so we don't have to beat that horse anymore. Gasoline is a solution primarily of octane. That's the chemical formula for octane. It's a hydrocarbon, right? Hydrocarbon. And it's the principal component of the gasoline in your tank. But most gasoline nowadays has some ethanol in it, up to 10% ethanol. Okay. Plus some minor components that the formulator of the gasoline says will keep your engine running clean, things like that, or improve the octane. All right, so gasoline is the only homogeneous mixture in that selection. So which of the following of these selections, A, B, C, or D, has every example is a pure substance? So if we find any mixtures in one of those, then throw it out. Oxygen. Oxygen as an element, it is a pure substance. Tap water. Tap water has dissolved solids in it, right? And it's probably got chlorine in it too. So I would say tap water is a mixture. Iced tea or a glass of tea. Oh, it's a mixture. Okay, so it's not one. Oxygen, glucose. Yes, glucose is a pure substance. Silver is a pure substance. I think we found our answer. Yeah, all of these three are pure substances. If we go to chocolate chip cookies or wood, they're mixtures. Dirt, rocks, they're heterogeneous mixtures. And gasoline's a mixture too, so all of those are mixtures. All right. So what's an element? Right, we've been throwing that word around as if we know what it means. An element, by first part of the definition, is an element is a pure substance. In other words, every component, every part, every little part of an element is identical and unique in its own right. They're all the same, but they are unique from all other substances. And there are no different substances mixed in. The identity of the element is unique for that element, and there's no way to separate the element by physical means. So that with that definition, being a pure substance, the only way that you can change the element into something different with a different identity is by chemical means. So any example in the periodic table is an element. Gold, my favorite. Silver. Actually, silver's my favorite. Gold's my second favorite. And that's a good note. We're not saying how much there is of it, right? When we say element, it could be a tiny speck, a gold flake, or it could be a gold bar, which I would prefer. Compound. What is a compound? Well, now that we know what an element is, a compound is also a pure substance because it has a unique identity and cannot be separated by physical means. It can be broken down by chemical means, but not physical means. And it must be a combination of two or more elements. This says simpler pure substances, but okay, I see what they're saying. That's correct. It can be broken down by chemical means into two or more simpler pure substances. It may not be elements that it's broken down into, but the only way you can break it apart is by chemical means. Right? But in effect, when you make a compound, you're combining two or more elements. Right? So if we say, if we look at this one, that's hydrogen gas. That's not a compound. It does have two atoms of hydrogen bound together, but it's still an element. So what we would do is maybe say this: two atoms of hydrogen and one oxygen atom gives you a compound called water. All right, there's another flow diagram. All right. Compounds are different than mixtures. Compounds are pure substances. Mixtures are combinations of pure substances. You can separate mixtures by physical means. You can't separate them by physical means if they're compounds, but you can decompose them, or you can change them by chemical means. Right? Also, compounds have a definite composition by mass. Now we're gonna talk about this in terms of the law of definite proportions, but this is a good place to make the point. Your pure substance will have a mass ratio of elements in its composition, and once it's identified as a compound, then no matter where you get that compound, where does it come from? Does water come from distillation, purify the water? Or does it come from reacting hydrogen and oxygen to get water? Once you've produced water, the ratio of hydrogen to oxygen is always the same, no matter what its source. All right. This is a decision tree for classifying matter. Right? I'm going to let you work that out on your own. These are just questions that you would ask yourself if you were classifying matter. Does the sample have the same properties throughout? Are two or more different substances present? Right? Can the pure substance, if it is a pure substance, can it be broken down into simpler substances? If it's pure and it can be broken down by chemical means, then it's a compound. Okay. The difference between an element and a compound. Well, an element can't be broken down into simpler substances by chemical means, but a compound can. Now, elements can be further broken down, but not by chemical means. You need nuclear means. In other words, physics takes over. And then we're starting to dip our toes outside the purview of chemistry. All right. Elements. We know of 118 elements. So if you look at your periodic table and you look at the one with the highest atomic number, it will be 118. Now, at one time, 88 of the elements occur naturally and 30 of them were man-made. Man-made. The number is shifting more towards naturally occurring and fewer towards synthesized. The reason being that originally the element may have been man-made, but over time, our analytical techniques have become more refined. We're able to detect smaller and smaller amounts of elements, even down to individual atoms. So now, the elements that we want synthesized, we're finding them naturally occurring in places that could not have been contaminated by our synthesized elements. So the ratio is shifting toward naturally occurring up to a point. Okay. When we look at the abundance of elements in the whole universe on an atom percent, that is, if we could count all the atoms in the universe, and then we count all the atoms separately for each element, we find that 91 out of 100 of those atoms will be hydrogen. So this is a good place to make the point. What do we mean when we say percent? If I just say percent, all it means is parts per hundred. So what do we mean by parts per hundred? It depends on the definition of the parts. If I say number of atoms per 100 atoms, in this example, I'm saying it's atom percent. Okay? If I'm saying it's so many grams of gold in 100 grams of ore, I'm saying it's mass percent of gold. Okay? So the problem with percent is if you don't identify what the parts are, then the percent doesn't tell you anything about the composition. That's the hazard of percent, and we're sort of stuck with it. Percent is grandfathered in to modern science. So it's important to know what we mean by percent. And we'll talk about it again later. But in this case, we're saying out of every 100 atoms in the universe, 91 of them are hydrogen. Why do you think that is? Well, because most of the universe is packed into stars, and stars are mostly hydrogen. And in fact, hydrogen was the first element that we believe was formed when the universe came into existence. And then a little bit of helium also. So out of every 100 atoms in the universe, you're going to find that 9 of them are helium. Right? Some of them, many of them were produced at the very beginning of the universe. And some of them are produced by nuclear reactions in stars as we convert hydrogen into helium. And that gives up a large amount of energy. That's why stars are hot. And that's why these reactions only occur in stars. We haven't completely mastered hydrogen fusion yet. We're working on it. We're getting closer to sustaining hydrogen fusion for energy production. But at this point, our best source of hydrogen fusion is in the core of a star. because the temperatures are high enough, pressures are high enough to promote the nuclear reaction. And then the rest of the universe, right? In this case, one atom out of every 1,000 atoms in the universe will be something else. So most of what we have in the universe, most of what we have here on Earth, concentrated in this ball, is represented by this very small percentage of the total number of atoms in the universe, right? So almost 100% of the atoms in the universe are accounted for by hydrogen and helium, with only a very small fraction being others. Now let's change our sample to the Earth's crust. And we're still talking atom percent, right? So out of every 100 atoms in the Earth's crust, and if you've had geology, you understand that the crust of the Earth is just that thin outer layer, right? You got the crust, and then underneath the crust is the mantle, and then underneath the mantle, and the mantle has structure also, underneath the mantle is the outer core, and then the inner core. But we're only talking about that very thin layer. It's like the onion skin on the Earth. And this is the composition that we find in the crust of the Earth. Now, I'm assuming that when we say the Earth's crust, we're not talking about the oceans. And if we do take that into account, then oxygen is the largest number of atoms. For every 100 sampled, 60 of them are oxygen. Okay, oxygen is a very common element in the Earth's crust. Very largely due to the fact that even if you don't have an open body of water, you have lots of moisture in the soils, in the rocks of the Earth's crust. That's one source of oxygen. Another source of oxygen is that the vast majority of metals that we find, and elements for that matter, that we find in the Earth's crust are compounded with oxygen. So when we produce, when we take iron ore and smelt it to get the pure iron out of it, we're removing oxygen, right? So iron ore, the part of iron ore that we want is this compound, right? So it's got lots of oxygen in it. And that's true for most metals in the Earth's crust. One exception is gold, right? Gold is what's known as a noble metal, and you can find it in pure form in the Earth's crust. Dig it up and run it through your sluice and collect the gold flakes or nuggets. But everything else is combined with oxygen. Excuse me. Let's see, 11 o'clock. Okay, I better get moving. All right, what about these other ones? Silicon is, out of every 100, you have 20 atoms of silicon. Many of the rocks and all of the soils have a large component of silicon in them, right? Sand on the beach is silicon dioxide. And the soils are actually silicon and aluminum, right? So aluminum is a very large component of the soils and the rocks for that matter. And then you have minor components from there on. All right, so major component, atom percent, is oxygen and silicon, accounting for 80%, and then 86% if you add aluminum. So which two elements dominate the Earth's crust? Right? Well, oxygen and silicon, and then the dominant one for the universe is hydrogen. All right, so I've been using chemical symbols, and we haven't really talked about where they came from. So we're going to talk a little bit about the history of the chemical symbol. When modern science and modern chemistry was starting to get its feet on the ground in the 17th century, and then into the 18th century. Well, by the 19th century, we were starting to accumulate various elements. We had identified elements. Several of them were already identified by alchemists coming out of the Dark Ages. But then we started to add to that list. We were learning to purify elements and determine that they were actually pure substances of a single type of atom. Well, it got to the point where we needed a way to organize our information, and rather than write out the whole name, we needed symbols, because it was rapidly becoming apparent that the language that we were trying to speak would be too cumbersome by writing out like this. If I were to write this, let's see, hydrogen, and then oxygen, and then hydrogen again, that would be water. This bond and that bond, right? That would rapidly become too cumbersome. So we needed a symbolic language, a symbolic alphabet for the elements that we were discovering and any future elements. Well, there were several proposals for what the symbols for the elements should be. And fortunately, there was a Swedish chemist whose proposal was accepted. I'm not sure how it was accepted, but it was the best one. There were some really wonky ones that came out, and it's a good thing we don't have to deal with those. So what we do is we take the element name, and for many of them, we use the first letter of the name. And if the first letter of your element is already taken, for instance, hydrogen. Hydrogen came first, right? It was discovered before helium. So hydrogen lays claim to a single symbol, capital H. And in any of these symbols, the first letter is always capitalized. So then helium, we had to go and add another letter. So we said He. The second letter is always small. If you write this for helium, it's wrong. And I will count it wrong. All right. So the symbols always are represented by either a single capital letter, or if that one's already taken for your next element, it will be a capital letter and a small letter. Now, many of them are derived from what we would consider the English name, but some of them are not. These examples: hydrogen, barium, Ba, cobalt, Co. Lead, where is Pb in lead? It's not. Some of the elements, the symbols are derived from the Latin name for the element. The Latin name for lead is plumbum. So we use P, B for that symbol. Now in Latin, plumbum means heavy. So that seems appropriate for lead. Silver, right? There's no Ag in silver. Silver is derived from the Latin argentum, Ag. And there are several others like that. You look at your periodic table, and as you're writing your, making out your flashcards, you'll see that occasionally you'll come across things like, I used one earlier, Fe for iron. Ferrum is the Latin for iron. That's where Fe comes from. And several of them are like that. That's making the point on this slide of the Latin origin. Okay, no new names. All right, so one or two letters derived from the element's name with the first letter capitalized and the second in lowercase. All right, that's true if you say the element's name can either be English or Latin. Now, we talked about elements. What we have to deal with now is, why is one element different from another element? They're both pure substances, but they have completely different physical and chemical properties. Well, we can go all the way back to the ancient Greeks for this idea of the atom. The ancient Greeks believed that everything, well, some of them believed that everything in the universe was composed of an elementary particle they call the atom. And it was believed by the Greeks, ancient Greeks, that there was only one type of atom, and everything was made of that atom. Right? They were okay about the idea of elementary particles, but when they said that all atoms are alike, they were painting themselves into a corner that they'd never get out of, because they had to do all sorts of mental gyrations to explain why you get this different substance if it's made of the same atoms as that substance. Right? So they invented other ways to deal with it. Fundamental forces or substances like earth, wind, fire, and water, and some other things that they tried to put together. It never did work. But the idea of the atom persisted. Right? It was picked up in modern times by an Englishman called whose name was John Dalton. By the way, in Greek, this word means. Let me get another marker. Can be divided into two parts. TOM means to cut. Right? Comes from tomos, which means cut. And A in front of any root word in Greek means not. It's just the opposite of. So when we say it's not cut, that means you can't reduce the atom any further. Can't make it any smaller. So that was an appropriate name, and it's good that we kept it. It is in effect the limit of subdivision. To make a pure substance, the atom is the smallest unit, and it is very, very small. Now, every element is made up of atoms, but different elements are made up of different atoms. Right? So when we combine atoms into units that behave as a single group, the identity changes from the components to the product. You have a molecule. So the best example of that is going from hydrogen and oxygen to water. These have their characteristics. Water has its characteristics. And it behaves as a single unit. Right? It's the smallest part of a pure substance of water that can be identified, that molecule, that can be identified as characteristic of that substance. Now, we can also classify molecules depending on how many atoms are contained in the molecule. And to do that, you add up the number of atoms. Right? This subscript here says that there are 2 hydrogen atoms. So we've got this 2 hydrogen atoms plus 1 oxygen atom means there are 3. And we use the Greek prefix for defining how many there are. Right? I don't have my hard copy, so I'm not sure if it comes up. The Greeks say that 1 means is meant by mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So if you put these prefixes in front of a root, you're saying there are that many of the roots. So when we say the molecule is triatomic, that means the molecule has 3 atoms in it. It's diatomic, it has 2 atoms. If it's tetraatomic, it has 4. It's pentatomic, it has 5, on down the line. Okay? We can also classify the molecule whether it has all the same element atoms in its makeup. If it's homoatomic, that means every element in the molecule is the same type of atom. So this is a homoatomic molecule of chlorine, but it's also diatomic because there are 2 atoms. It's a diatomic, homoatomic molecule. Phosphorus, this example of phosphorus, it's tetraatomic, but it's also homoatomic because only has phosphorus atoms in its makeup. And then there's 1, 2, 3, 4, 5, 6, 7, 8. This is octaatomic because it has 8 atoms, but it's also homoatomic because it only has 1 type of atom, sulfur. Now, if we have 2 or more types, then you can say it's heteroatomic. So water, our example before, is heteroatomic. It has hydrogen and oxygen. Homoatomic molecules are always elements, right? Because they are not combinations of 2 or more different elements. So homoatomic molecules are always elements. Heteroatomic molecules are always compounds because they have 2 or more kinds of atoms, right? So this one is diatomic and it's heteroatomic. This one's triatomic, hetero. This one's tetraatomic, hetero. This one's tetraatomic, hetero. So classify xenon tetrafluoride. I named a compound. I haven't told you how to name compounds yet, but that's what its name is. So is this a diatomic, triatomic, what? It's 4 plus 1 is 5. It's pentaatomic. Right? Is it homo or heteroatomic? Well, it's a compound. It's heteroatomic. Is it an element or a compound? We already said it's a compound. Okay? Now, it may seem strange. Xenon is a noble gas. And noble gases tend not to form compounds. But the larger ones, xenon and krypton, have been forced into compounds. They don't naturally occur that way. All right, which of the following statements is true? The smallest particle in an element that can exist and still have properties of the elements called the atom. Oh yeah, that is true. Well, all of them are true. I gave away the answer. A group of 2 or more atoms that function as a unit form a molecule? Yes, indeed. Some classifications of molecules are diatomic, homoatomic, heteroatomic. That's all true. So when we write a chemical formula, let me back up. When we write the symbol of an element, and I'm going to use X for the symbol. I can't use Xe because that's xenon, right? But X is not found anywhere on the periodic table, so this represents a generic element name, symbol. So there are 4 positions around that symbol that we have reserved for specific information. We've already looked at one of them. This is the number of atoms. Okay? You want to say how many there are? Put a number there. If you don't have a number, then there's always one, because the symbol's there. That means there has to be at least one. So we're not redundant. We don't put in a one when there's when there's a symbol there and we only have one of them. Up here we have the charge. So if we take an element and strip off an electron, say, just for example, we make an ion, and it's going to be a +1 charge. Right, so that's where the charge is located. It can be +1, +2, +3, or -1, -2, -3, whatever the case may be. If there's no symbol there, if there's no number there, then it's neutral. It has no charge. You don't have to put a 0. On this side, this position is reserved for the atomic number, which equals the number of protons. And we haven't gotten that far yet, but when we get there, that's where we put the number of protons. Up here, by that symbol, we have the mass number. Mass number is equal to the number of protons plus the number of neutrons. All right. So just keep that in the back of your mind, these two, because I haven't described the structure of the atom yet, right? Where the protons came from, where the electrons came from, where the neutrons came from in historical context. But as far as writing the compound, right, when we say H2O, that means this molecule has 2 atoms of hydrogen, 1 atom of oxygen. Now this one is complex. We definitely have 3 atoms of calcium. But with this PO4 in parentheses with another subscript means that that 2 is multiplied by everything inside the subscript. So in fact, we have 2 phosphorus atoms and we have 8 oxygen atoms. Okay? All right. How many atoms of each element are present? All right, we just count them up. 2 hydrogens, 1 sulfur, 4 oxygens is 7. Okay. This one we have 2 irons. We have 3. Count on my fingers. We have 1, 2, 3 carbons, and we have 9 oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 14. All right. So the chemical formulas consist of our chemical symbols and how many of them there are of each in the formula unit. All right. I'm kind of running short of time, so so that I don't lose. I'm going to let you work this one out on your own. An electrical current is applied to 50 milliliters of water. After a period of time, there's nothing left in the container because when we insert an electrical current, a direct current into water, it supplies energy to break bonds. And the water is broken apart. This is a chemical change from water to hydrogen and oxygen. So when we make hydrogen and oxygen now, they become a gas and they escape. And eventually there's nothing left because we have converted all of the water into hydrogen and oxygen. That's why this is the answer. And then 2, let's see, you're given 2 cylinders, each containing a gas. You're requested to test flammability. You discover that one gas is very flammable, but the other extinguishes the flame. The 2 gases are this one and that one and are classified as this one and that one. Okay, you're given 2 cylinders. So what could they be? Well, if one of them smothers a flame and the other one is flammable, then we can't have hydrogen and methane because they're both flammable. Right? We can't have neon and carbon dioxide because they're both inflammable. Non-flammable, excuse me. Inflammable is the same as flammable. Non-flammable means that they don't burn. So we can eliminate A and we can eliminate C. Hydrogen and oxygen, right? Hydrogen burns. Oxygen doesn't smother the flame. It doesn't extinguish. It supports the flame. So based upon that, D, C, and A are thrown out, and B seems to be the answer, right? Hydrogen and carbon. And let's see if it's true, right? The first one is diatomic. Yes. Hydrogen in its most common state at room temperature and pressure is diatomic. It's two hydrogen atoms bound together. Carbon dioxide is heteroatomic. It's a compound, right? Okay, so there's your answer there. And now we can move on to chapter 2. So now we're ready to get chapter 2. We've been introduced to the components of chemistry and its language. Now we want to look at, well, measurement. Whenever you conduct an experiment in chemistry, or in any sciences, actually, eventually you're going to make a measurement. Now, you may be able to make qualitative. Let me erase this. You may be able to make qualitative observations. Observations, such as the sky is blue, or the grass is green, or something stinks. But science usually hinges on quantitative observations. And that means measurement. You're going to have a number and a unit of measure also. So we're going to talk about that coming up. So here's, when you make a measurement, you're saying two things about the object that you're measuring. One is your units of measure. How big are your units of measure? Are they little like that? Or are they big like that? Or even bigger? And then, how many of those units are you assigning to that measurement? So if I say, if I tell you, I just say, I am 71. You're automatically going to assume that I say, I'm 71 years old. Well, not quite, 25th of this month yet. But if I say that, that doesn't give you enough information. Not as a scientist, it doesn't. 71 means nothing without the units of measure. So what do I actually mean? Well, let's say I do mean I'm 71 years old. Now the units of measure tell you something that the number doesn't. Okay? If, on the other hand, I said I'm 71 inches tall, that changes the entire meaning of the measurement. Now it's not how old am I, it's how tall am I. Okay? And that one's correct. I'm 5 feet 11 inches tall. That's 71 inches. So both are accurate. Well, this one will be accurate in a few days. 6 days. Right. So every measurement has a number and a unit of measure. And the unit is what we identify as the scale. Are we using a small scale or a large scale? All right. When we express these values with their units of measure, we're going to focus now on just the numbers, right? Because we need to get a handle on numbers that are very, very large or very, very small. Because standard notation is not always the most convenient way to express a value, a measurement. In this case, we have 93 million is our standard notation. And what we want to do is use a technique for condensing that number, but retaining all the valuable information in the number. Okay? So we have a system called exponential notation. And all exponential notation says is we can take a large number in the decimal system and we can say, all right, if the standard notation is this number, I can express it by splitting it into a multiplier, right? Something times something else. And the something is the coefficient. And the something else is the power of 10. Okay? So this number that I represent down here is still the same as that. It represents the same value, but it's more convenient. It's compact. So how do we store up information in this value? Well, there's a decimal here. We understand a decimal to be right there. So if we say this is ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions position, then as we move the decimal to this side, it makes this part of the number smaller. So we're storing up information in the power of 10. We're storing up a power of 1. We're storing up a power of 2, of 3, of 4, of 5. Let's say we store up a 5 and we move the decimal to that position. Now the part of the number that goes into this position is 930. And the part that goes into this position is 1, 2, 3, 4, 5. That would be exponential notation. This coefficient can be any size you want it to be. Okay. What we've got here is a special case of exponential notation called scientific notation. Scientific notation goes one step further. This number, the coefficient, must be 1 or greater and less than 10. So between 1 and 10 has to be the coefficient. So in order to do that, we need to take that decimal and move it 2 more places, which now means that we've got 10 to the 7th times 9.3. Okay? This is scientific notation. All right, that's the difference. I'll explain later why all of these zeros went away. In scientific terms, they're not significant. Right? We'll talk about significance in a few minutes. But they went away, and all we're left with now is 9.3 times what this means. 10 million is 10 to the 7th power. Okay? And to prove it to yourself, just expand it, right? What is 10 to the 7th? Multiply by 9.3, and you should get that number, right? Check your work if you want. It's always good to think about your answer. After you give the answer, say, is that a reasonable answer? If it's not reasonable, that should be a clue that maybe you did something wrong, right? If I were making a calculation and the calculation came out to 115 billion, but it was supposed to express the size of a gnat. You know, a gnat is what, 115 billion meters? No, that's unreasonable, right? So you should always be aware of the outcome of your product, whether it makes sense, whether it is reasonable. All right. So this is a good question. What happens if your coefficient is 10? It can't be 10. It has to be less than 10. So if we had a number like this, let's just, for argument's sake, say our number was 10 times 10 to the 5th. We can't have a 10. We have to store that information in the power of 10. 10 to the 6th times 1. Okay? All right. Let's see. Yeah, I'm scooting a little bit there. So, we just condensed a very large number into scientific notation. You can do the same thing for very small numbers and put them in a manageable size. Let's see. Going to get an example? Or do I have to make one up? Yeah, I think I'm going to have to make one up. All right, so if we have a very small number, it would be a decimal fraction. Say we had 0.0000009.3. How about that number? We can store that one up. We can convert that one to scientific notation. All we have to do is say, are we storing up positive powers of 10 or negative powers of 10? If we move the decimal this direction, we're storing up negative powers of 10. So 1, 2, 3, 4, 5, 6, 7 to the minus 7 times 9.3. All right, that's what a small number looks like in scientific notation. I'll also make one other point. Let me use a simpler example. Say we have 0.093. Right. Let's use this number. If you write this number on a graded product and you write it like this, it is wrong. That decimal must be bracketed by another 0. I call these orphaned decimals. Some people call them dangling decimals. So don't make that mistake. If you learned it that way in grade school and high school, then I'm not going to apologize to the teachers that taught you that because they're wrong. Okay. So these are just hints as to how to store up information. One thing you will notice is this is a very small number, right? So if this small number is converted into a larger coefficient, if the coefficient is larger than the number, then the power of 10 must be negative. On the other hand, if we have a very large number and we store up a smaller number in the coefficient, then the power of 10 must be positive. Those are just indicators that you're moving the right direction with your powers. All right, so here's another example. All right, we move the decimal to the left, that stores up positive powers of 10. If we move to the right, that stores up negative powers of 10. All righty. Which of the following correctly expresses 7882 in scientific notation? All right, so we got a decimal that's understood to be just to the right of the 2. If we move it to the left, we're storing up positive powers of 10. Why? Because the coefficient is shrinking. It's getting smaller. So the powers of 10 must be bigger, positive. So we're going to move 3 places to the left. And that means we've stored up 3 powers of 10. But the coefficient now is 7.882. There you go. I think the next one is, yeah, it's a small number notation. So we're moving to the right, 1, 2, 3, 4, 5 places, -5, and we're left with a 4.96 coefficient. There it is right there. Okay. Okay, we've already mentioned this. Quantitative observations consist of two parts, the number and the unit. And these are examples. Right? We have to learn something about the units of measure. The reason for that, well, it could be personal and it could be public. Personal is you want to have a way to understand your own work, right? So you need to know what the unit of measure means. But also, once you finish your research, one of the points of doing research is that you spread that information out to the other scientists in your community. That's called modern science, right? Before modern science, if you discovered something unique and you had that knowledge, that was power, and you kept it to yourself. You only gave it to somebody else if they were apprenticed to you. And then your apprentice could learn what you knew, but you rarely shared your private knowledge with other people. Now, there are exceptions, of course. Otherwise, where would alchemy come from, right? if I don't have some experience, I would have to be apprenticed to some other alchemist, and then I could work on my own projects. But you want to define the unit of measure. So we have to agree upon what that unit means. And we're going to get to that in just a second. But when you write it, the unit of measure, in this case, is written out as grams. It's abbreviated as little g. But the unit of measure can be compound. And the way you compound one is like, let me use an example. Say the speedometer in my car is broken, and I want to know how fast I'm going. So I'm on the interstate, and you know the mile markers, right? You can tell how far you've gone. Or you can say your odometer is not broken, and you can read how far you've gone off the odometer, but the speedometer is messed up. Or you don't trust either one, so you're going to use the mile markers. Well, let's say I move 1 mile, and on my watch, so much time has elapsed. Say 60 seconds has elapsed. In 60 seconds. Okay. How fast am I going? Well, my speed, my velocity is I go 1 mile in 60 seconds, right? So notice we've got a quotient here. 1 divided by 60 is 1/60th, right? Well, the thing about science is when you divide the numbers, you also divide the units of measure. Or when you multiply numbers, you multiply the units of measure. So now the units of measure is miles per second. 1/60th of a mile per second is my speed. Now later we're going to show you how to convert that into miles per hour because you understand what miles per hour means. But miles per second doesn't mean as much. So here's a compound unit of measure. A joule is a measure of, excuse me, heat, and seconds is time. All right, so we need a way to standardize units of measure. And this is the common system in use today, the international system, or in French, Système International. Right, the French do everything backwards, so that's why it's SI and not IS. All right, so these are fundamental units. These are units that have a standard. Somewhere, a physical standard that we can compare our units to theirs, our measurements to theirs. Right? So the mass kilogram is the standard mass. And it's represented by a platinum iridium cylinder, which is very resistant to corrosion. And it's preserved in a cave in France. And they use a cave because the temperature is constant all year round. And it's inside a double bell jar filled with argon to protect it. If you want your unit of kilogram standardized, you send it to them, to the measurement body, and they will compare your kilogram to their standard and tell you how much yours actually has in mass. They may send you a report back and say, yours is a little bit heavy. It's 1.00000003 kilograms. Originally, the standard of length, the meter, was also a platinum iridium bar. It had a certain type of shape that would prevent it from warping. And you would compare that. Now, the meter itself is derived from a measurement on Earth, right? If you know anything about latitude and longitude, the zero longitude runs through the Royal Observatory in Greenwich, England. That's the zero longitude. Then you measure everything east or west of that. Well, if you go from the North Pole to the equator through that 0 point, that is a certain distance. And that was an accepted value at the time, and they just took a fraction of it to make the meter. And then once they standardized it, that was chiseled in stone, or actually chiseled in platinum iridium. Nowadays, though, if you've got the money, you can buy a scientific instrument that will create a meter or measure an exact length relative to this standard using laser light. So you don't have to send your meter stick to France to get it standardized. Time, the standard of time is the second. That's the fundamental unit, the second. It was grandfathered in from ancient times, and it was derived from astronomical observations. So what we had to do was take what was generally agreed upon length of time and standardized it. And now we have access to very accurate measurements of that second using atomic clocks. In other words, the radioactive decay of a certain isotope is used to time the clock, and that fixes the second very accurately. We need that, right, more now than ever, because our satellites in space need to know exactly what time it is to determine where they are. And especially for the GPS satellite system, they need to know where they are so that when they send a signal from 3 or more satellites to your receiver, that it's able to rely upon their position to calculate your position on Earth. All right, standard of temperature is the Kelvin, right? It's related to the degrees Celsius, and we'll talk about that later. Electric current is the ampere. It's a standard, but we're not going to use it, right? Because this course doesn't go into enough depth to use it. The mole we are going to use. The mole is simply a counting, a number of things, amount of substance by counting them. And there's a number associated with it, and we'll talk about that later also. All right. Now, here's the problem. We've got these standardized fundamental units. The problem is those fundamental units might be too large or too small for the measurement we want to make. So we need prefixes to modify our unit. I'll use this one first, the kilogram. That's the fundamental unit, right? But it's built of a prefix and a fundamental here. Not a fundamental, a base unit. This is the gram. The gram was inherited from alchemists. And it was understood to be a certain size, a little small thing. So the problem with standardizing a small thing like that is that if it's scratched or gets a fingerprint on it, or it's adulterated in any way, the percentage error is huge. So to remedy that situation, we said, okay, the gram is here to stay. Right? So our standard now, our fundamental is going to be 1,000 times that. So we can make it big enough to handle. So that's why the fundamental unit is actually a prefix of a base unit, the gram. Well, the kilo still means 1,000. So the kilogram is 1,000 times a gram. And there are other measurements. You can make smaller measurements also. All right. Say we have a centimeter. Right? Everybody's heard of centimeters. Well, a centimeter is 1/100th of a meter. So when we say this, we're saying this part is 1/100th of that part. So now we have a different unit. Millimeters, we've heard of those. Micrometers, we've heard of those. If you've ever worn sports clothing these days, brand new sports clothing, it probably has nanofibers in it, right? From nanotechnology. That's where the name comes from. 1/1000th of a meter is a nanometer. All right. So if we say we're going to travel 100 kilometers, our unit of measure is the kilometer, and we're going to go 100 of those units. What if we wanted to go a distance in meters, and we say it's 100 kilometers? Well, it'd be 1,000 times that, wouldn't it? Right? If we said 100 kilometers, well, take that kilometer, and that kilometer is 1,000 times a meter times 100. Right? So that's 1, 2, 3, 4, 5. That's 10 to the 5th meters. Right? We've still gone the same distance, but we're just using a different unit of measure. So when we change the unit of measure, the number changes too. Notice that when the unit of measure gets smaller, the number in front of it gets bigger. Right? Smaller units of measure, I mentioned these already. Right? These prefixes mean a certain thing, and they change the unit of measure attached to your number. Volume is, and these are derived units. When we use a prefix, those are derived units. Some derived units don't have prefixes because we've accepted a unit that is related to the fundamental. Right? So if the fundamental unit is a meter, then we have a cube that's a meter on every side. That means we have 1 cubic meter. So how many, let's see, if we take one side and subdivide it into decimeters or tenths of a meter, right? We have 10 of these blocks on this side and 10 on that side and 10 deep, right? So that means that this one would be a decimeter on one side, and the cube of that decimeter gives us a new volume. 1 cubic decimeter has been accepted as 1 liter. Okay, so now that is not a fundamental unit, but a derived unit. We might call it a base unit. Right? So now that we have this one, if we blow this one up now to this is a liter, and we take a tenth on this side, well, a tenth of a decimeter is a centimeter, because a decimeter is a tenth of a meter, and a tenth of a tenth is 100th. So 100th of a meter is a centimeter. If we cube that one, now we have a cubic centimeter. But notice in this liter, we have 1,000 centimeters. All right. So if we have 1,000 centimeters, then one of those centimeters is 1,000th of the original, which is a liter. So 1 centimeter, cubic centimeter, is 1 milliliter. Milli is 1,000th of a liter. So they're all related by these prefixes and by established base units. Remember this one: a cubic centimeter and a milliliter are the same. Because if you find yourself with a calculation that is based upon some length, and you end up with a cubic centimeter in your unit of measure, but in order to go further with it, you need a milliliter, then you just substitute a milliliter for the cubic centimeter because they're exactly the same size. All right. Mass. We can measure mass very accurately. Now, in my lab here at New River, my lab has an analytical balance that will measure to 4 decimal places, or 1/10,000th of a gram. Very accurate. And this is in a student lab. The lab at Logan for Southern, we have 2 top loading balances that will measure to 1,000th of a gram, 3 decimal places. There is an analytical balance in that lab, but it doesn't work. Right? It's broken. So we're kind of stuck with 3 decimal places instead of 4. The SI unit is a kilogram, right? The fundamental unit is a kilogram. And we have conversions, equalities. We can equate a kilogram to 2.2 pounds in a different system, in the English system. Now, the problem with that is let's see, 046. The problem with that is this is apples and that's oranges. This is mass and that's weight, right? And they're not the same by definition. But this equivalence works only if you're in Earth gravity. Because weight is based upon whatever the mass produces as a force on the surface of the larger mass as a consequence of its mass and the gravitational field. So on the surface of the Earth, this equation works. On the surface of the moon, it wouldn't work. In fact, on the surface of the moon, it would be divided by 6. But that brings us to the definition of the balance, right? The laboratory balance is based upon comparing masses and the forces that they exert on each other in 1G. So if both of these masses are in the same gravitational field, we can compare their forces and equate that to their masses. So in the balance, we're going to work with the balance in the lab. It's one of those balances like you see in a doctor's office, where you slide the weights back and forth. You're comparing forces. The force in the pan is one thing, and the force that you're applying on the balance arm is adjusted so that they're equal. And once you can read the force in the balance arm, you can equate that to the unknown. So as long as we're in 1G gravity, we can make this equation, if this equivalence work between mass and weight. Or we could do the other way, right? We could say 1 pound is 453.59 grams. Those can be manipulated into conversion factors so that we can take any value we get for kilograms and convert it into pounds. or any gram we get for grams, any measurement we get for grams, and convert it into pounds. All right, we'll talk about conversion factors in a few minutes. Okay, which one of these doesn't make sense? This speaks to the ability of the scientist to develop an intuition, right? What makes sense? A gallon of milk is equal to about 4 liters of milk. If you have an idea of what a liter is, right, you can buy liter bottles of pop, right, like that. If you put 4 of those together, is that going to look like a gallon of milk? Well, yeah, it's pretty close. Even better, if you walk through the grocery store, read labels. I always read labels. Ingredients, composition, right? Measurements, nutritional values, even English versus metric weights and volumes, because they're all printed on our labels now. It's not just English units anymore. It doesn't say 1 gallon. It also says what is that in liters. So if you look on a gallon bottle of milk, it'll say 3.8 liters. That's about 4 liters, right? How about a man, 200-pound man has a mass of about 90 kilograms. Use your conversion factor. If about 2 pounds is a kilogram, then 2 into 200 is 100, and that's close to 90 kilograms. So yeah, we can say that's reasonable. We're using a procedure called estimation. Estimation is a very good habit to get into so that you can keep your calculations honest. A basketball player has a height of 7 meters. Right? How big is a meter? Well, if I put one end on the floor and the other end up here, it'd be about like that. Stack 7 of those high. Is that the height of a basketball player? No, not yet. I mean, some of them are pretty tall, but not 7 meters. That's not reasonable. How about a nickel? Is it 6.5 centimeters thick? What does a centimeter look like? Well, a centimeter is about like between those 2 lines. If you put 6.5 of them together, you're saying your coin is that thick. It isn't. That's not reasonable. Our unit of measure is probably in error. If we said 6.5 millimeters, that might be closer to the truth. Or if we changed meters to feet, that might be a better estimate of a basketball player's height, 7 feet. Now, I could believe that. So those 2 are false as given. All right. Here's a very, very important concept. It's called uncertainty or error. Every measurement you make has built-in uncertainty. You may think that you measured something to be 25 centimeters long, but there are numerous ways in which that value can be in error. So what we have to do is we have to analyze, we have to investigate what are the sources of error and how do we express our values so that we can take those errors into account and keep us honest in our conclusions that we draw from the results of our experiment. So every scientist knows that when he or she sees a number written, it's written this way. For example, if I write that number and it has a unit of measure attached to it, which is not important right now, that scientist knows that I'm claiming those digits are certain. They can't be anything else but those values. That's what I'm claiming. The last one I'm claiming is uncertain. And that's a fancy word for saying it's my best guess. Okay. So in this example, we're trying to bridge the gap between that intellectual concept of uncertainty and what does it actually mean when you're making a measurement. The certain digits are those that are derived from your measuring device that is calibrated for those values. So it's calibrated, in that case, it's calibrated all the way down to the tens position, but not the ones position. So the ones position is a guess. So in this case, if we're looking at a ruler, we say that's 1 centimeter, that's 2 centimeters, that's 3 centimeters. But the nail extends between 2 and 3. So we know that the first digit is going to be 2. And the unit of measure is going to be centimeters. So it's between 2 and 3. Now let's go down and look. All right, let's look at it closer. We find out that it's not just between 2 and 3. It's down here around 0.8 or 0.9. So it's between, it looks like it's between 0.8 and 0.9. So when we blow it up, this line represents 0.8 and this line represents 0.9. So we know that we've exceeded 0.8, but we're not to 0.9 yet. Now we have finer scale that we can't see in these pictures. But the finer scale says, okay, this scale is 1/10 of a tenth. So 1/10 of a tenth is 100th. So it's 0.0 something added onto this, right? So we're going between 0.8 and 0.9. So that's 0.8, 1, 2, 3, 4, 5. 0.85. Now I can claim those as certain digits because this device is calibrated down to that level. But if I report my number this way, anybody who reads it is going to say, that's uncertain. But it's not, right? It's certain. So what I have to do is, since it looks like it's right on 5, I have to make this guess a 0. All right. All right. So the mistake in this slide is that reporting it as 2.85, I'm saying this number is saying that the certain digits are 2.8 and the uncertain is 0.5, is 0.05. And that's wrong. This slide is wrong, right? It should have had a 0 out here. All right. Now that's one way to handle, to understand uncertainty or error in measurement. Here's another way. If you have an idea of what the value should be, we often call it a true value. More often than not, it's an accepted value. Then we're saying that if your measurement is very close to or right on that accepted value, then you are producing an accurate measurement. Accuracy, right? So if we look at it in terms of a target, something like that, then if it lands here, that's accurate. Precision, well, and let me back up. Accuracy can either be a single measurement or several measurements of the same property. So if we hit the first one right there, that's good. It's accurate. But suppose we have one here, one here, one here, and one here. Then the average of those values makes it about right there. So that's reasonably accurate. for the average. Okay. Now let's talk about precision. Precision and accuracy are very often in the popular media equated. When they say something is very precise, what they mean is it's accurate. So we have to clarify our language and use it properly, because the rest of the world is not going to. Precision speaks to the grouping. How close are series of measurements? Repeated measurements. If the repeated measurements are grouped very closely, then you're saying this is a precise measurement. So if we had one here, one here, one here, and one here, right, that would be precise. Say you're a hunter, right? And it's right before hunting season. You've had your rifle in storage for 6 months, and you want to check out your scope to be sure your scope is sighted in properly. So you go to the range and you set your target out at 100, 200, 300 yards, whatever you expect to your quarry to be located at, and you fire 3 or 4 shots. If they land like this in a tight grouping, that's good. That's precision. That's good precision in the whole mechanism of your rifle. But it's not going to hit the target. It's not going to hit where you want it to. So you dope your scope. You make adjustments, and you bring that grouping down to here. And then you fire 3 or 4 more shots. And if they are still in that tight grouping, you're ready to go. Go 30 degrees or 25 degrees in the morning, sitting in your deer stand waiting for some deer to go by. Right? That's not for me, but some people like it. So in that case, you've got both precision now and accuracy. Right? I've got some examples here. So this one is an example of an accurate average value, but not precise, because there's a lot of scatter. This example shows that you've got not accurate, but reasonably precise, because the average puts it close to the bullseye. This one is like our sighted-in rifle. It's both accurate and precise. And then the last one would be what? Not precise and not accurate. Right, there you go. These guys are scattered all over the place, and their average is down here somewhere. All right. Now, I mentioned significant figures earlier. Let's talk about them in detail now, because there are rules that we use to count significant figures in a number. And the reason we're using this method is not just so that we can say we know how many significant figures are in that number. We're using it so that when we combine 2 or more numbers together in a calculation, we have a method for determining the number of certain digits that we can keep in our answer. So we have to learn how to count significant figures first, right? And so there are rules involved. The first rule is the easiest. All non-zero integers are significant. So if you have a 3, 4, 5, 6, you've got 4 significant figures. Okay. The next rules reference what do you do with zeros, right? As far as counting them goes, there are 3 types of zeros that can be in a number. The first type is a leading zero. one that's to the far left, right? And it's to the far left of all non-zero numbers. Okay. These never count. They're never significant. They're just placeholders, right? So for this number, which is written correctly, it's got a 0.048. Those two zeros are not significant. Those two non-zero numbers are. So this number has two significant figures. Then there are captive zeros, those zeros that are stuck between non-zero numbers. Now you can have one stuck between non-zeros, you can have two, three, you can have a whole host of zeros stuck between non-zero numbers. Suppose we had this number that we looked at before. Now, all of those zeros are significant. Whereas before, we just threw them out because they weren't significant. Okay, so that zero is significant. This number has four significant figures. And then trailing zeros are significant. Right, we have no trailing zeros here anymore. Let's do it like this. Let's put this zero back. Now we know that those trailing zeros are not significant because there's no explicit decimal point. If we wanted them to be significant, if we meant them to be significant, we put a decimal there. Now, that has 3, 4, 6, 7, 8. That has 8 significant figures in it. This one has 4 significant figures. This one has 2 significant figures. If we wanted that one to be significant for 3, we would put a decimal out there. Now, the reason that the rule I gave you on bracketing decimals with zeros, we can't use it here. In other words, we write this one. If we meant that zero to be significant, we'd have to do that. And we can't put a zero out here. Why? Because if we put a zero out there, now it's got 4 significant figures. So we're kind of stuck in a conundrum. What do? Well, you just have to be careful, right? Because that decimal point could be mistaken as the period of a sentence. Right? If we had a sentence out here and it ended with that number with a period, which is it? Is it the period at the end of the sentence, or is it the decimal in the number? Right? So that would be a real problem. All right. And then there's one other type of number. It's called the exact number. These numbers have no limitations on their significant figures. So when they enter into a calculation, they have no impact on the product, the outcome. And they come in 2 flavors usually. They're either conversion factors coming from an equivalence like this, or they're counting numbers. 9 pencils, 5 fingers, 2 eyes, whatever. Counting numbers are exact numbers. All right. We already talked about exponential notation, but the nice thing about exponential notation is if you do it right, then your coefficient preserves the number of significant figures in its value. So this one has a 300 with a decimal. That means we keep both of those zeros. If it was 300 without the decimal, then it would just be 3 times 10 to the second. Right, I mentioned that already. Number of significant figures is easily indicated in the coefficient. And then those zeros that are insignificant, you just get rid of them. Right, so 93 million with no decimal at the end is reduced to 9.3 times 10 to the 7th. Now, here's the problem. We do calculations. We may write it on paper, but we don't typically do calculations longhand anymore. I do it sometimes just to stay in practice, but we use calculators. Well, calculators can't be programmed to take significant figures into effect. Now, larger computers, if you use a program with an algorithm in there that will do this for you, yeah, you could do it that way. But we typically use hand calculators, and the output is going to be dictated by you in the display as so many digits, right? So when you punch your calculator, your values in, it's going to spit out as many as you ask for, right? And that's probably more than you're permitted to keep in your answer. So we need to know how to round numbers down to the number of significant figures that are permitted in your answer. Well, we're going to keep it really simple, right? If you have a number that is, let's see, 257.94, something like that, and you know that you can only keep 4 significant digits in that number, and it's got 5 now, then you go to this position, which is 1, 2, 3, 4, and you look immediately to the right and ask yourself, is it less than 5 or greater than equal to 5? This one's less than 5. So that means this one is rounded down to 0, and this one stays the same. Well, actually, what did I say originally? You could only have 4 significant figures. In that case, that 0 goes away. Okay? So that's the rule. It's based upon 5 or greater or less than 5. And you always look immediately to the right of the number that you're trying to round. You don't round, say if this number was out here, you don't round until you get to the one you want, right? That introduces significant rounding errors. So you look immediately to the right of the one you want to round, and that answers the question. All right. Let's see. This is a rule that I invented. We're going to encounter 2 types of calculation that need to be evaluated in terms of significant figures: multiply, divide, and add, subtract. If you have a series of calculations that are all multiply, divide, then you can do that multiplication and division all the way to the end, and then use the rules that I'm going to give you in a minute to round off the answer. So keep that rule in the back of your mind. Now we got mathematical operations. Like I said, we've got 2 flavors. One is multiplication, division, and the other one is add, subtract. These also refers to powers, because taking the power of a number is simply multiplying it by itself several times. So if you have a multiply or divide situation, the rule is simple. Whatever your calculator tells you as an answer, you look back to the multipliers or divisors in the operation, and you look for the smallest number of significant figures. This one has 4, that one has 2. The answer then can only have 2 significant figures. So you count from the left, 1, 2. That position is 3. To the right of the 3 is greater than 5, so 3 becomes 4, and the 8 1 drops out. That's why the answer is 7.4, with 2 significant figures equal to 2 significant figures in the least of the operators. And then, of course, if you have a series of multiplications, if you have that times that times that times that times that times that times that, just do them all. And then look for the smallest one in the series to find your answer. The reason for that is if you multiply A times B times C times D equals E, and you do this one and round up, right? You have to round up for that one. And then you take that product and you round up here. And you take that product and you round up here. You've been rounding up and up and up. You're going to have a significant rounding error in your answer. So do all of them, then round. And you eliminate that problem. Now, add subtract is a different animal. If you've got add subtract in all of your operations, they have to be done separately. And they have to be done in proper order. Right? Every math class tells you the order of operation, right? Order of operation follows this. Everybody has seen this one. If there are parentheses, that's great. Parentheses direct your calculations, right? That's what P stands for, parentheses. Once you've got the parentheses done, then you look for exponents. And then the next thing you do is multiply, followed by divide, followed by add, followed by subtract. So if you've got add, subtract in there somewhere, and you've got parentheses, great. It's going to tell you what to do first. And then once you get to add, subtract, you take the values that you get from the other operations and you put them into this rule. And here's an example. Say we have, we're going to add 23.445 to 7.83. Right? This one has 5 significant figures, 3 significant figures. What you do is you line up the decimals. Right? Then you add 5, 7, 12, carry the 1, 10, 11, carry the 1, 3. That's what you would get longhand adding those two together. But you are limited to the least number of decimals in the operators. This one only goes to the hundredths place. So your answer can only go to the hundredths place. So you have to round to this position. There's 5. That means you drop it and round 7 up to 8. That's why the answer is 31.28. And it has 4 significant figures, whereas your operators had 3 and 5. Right? So you can only tell how many significant figures are in your answer by actually doing the calculation. All right. Let's see. Okay. Yep. All right. I wanted to make another point. Suppose you have numbers that don't have explicit decimal points. Right? Say we have, let's use those numbers. 2, 3, 4, 5, 5. And we have 7, 8, 3, 0. Add those. Okay. Well, there's an understood decimal place here and here. But that one doesn't have a decimal, explicit decimal. So the rules of significant figures say the position that we have to rely on is over here, not there. So when we add them together, right, 2, 1, 3, we have to draw the line here, not outside the 0. If there were a decimal here, then we could use all of it. But since there's no decimal, then we have to round this one to 31, 3129. And since this is the ones place, we have to put a 0 there as a placeholder. Otherwise, we would think this was 3,129 when no, it's 31,290. Okay. But that's not significant because we don't put a decimal there. All right. Now, when you've got a series of operations and one depends on the other, In this case, we're using a measuring device here and a measuring device here. And what we want to know is how accurate, or what, when we use our add rule, when we add these two volumes together, what can we claim as the total volume? Well, the short answer is your volume accuracy is dictated by the least accurate device in the sequence. So this one is going to limit the accuracy of the device. Even though this one is much more accurate, you're combining it with this one and you're suffering the consequences. Right? So the total volume, we're going to have, let's see. Well, they did ahead and did the calculation. This is going to be 1, 2, not 3. This is 0.2, 0.4, 0.6, 0.8. So it's like 2.8. And then if we add our guess, it's sitting on 2.8, but we're going to say 2.80 because we want the last one to be uncertain. So 2.80 for the big one. And for the little one, we've got 0.280. So when we add them together, it's like that. And we have to limit there, so that one goes out. So our answer is actually 3.08. So this slide is also in error because it says 3.1 is the best you can do. But using our rules and what we know, 3.08 is the accurate volume. All right. Now what we want to do is be able to convert units from one measuring system to another, or within a system, we can convert units from one measuring or base unit to another one, or derived unit. We want to convert derived units. In order to do that, all we need is a statement of equivalence, right? That's like an example. We know that 12 inches equals 1 foot. And those are exact numbers. Right? Once we have that equivalence, we can use that information to construct a conversion factor that will allow us to convert units in a measurement from one size unit to a different size unit. All right, so here's how it works. This example, a golfer has a putt on a green that he estimates at 6.8 feet, or maybe he measured it, I don't know. So we want to know how many inches is that. So if you're starting from 6.8 feet and you want to end up at inches, right, something in here, you need a multiplier that will not adulterate the calculation and give you the units you want. So in math, we know that if you multiply anything by 1, that's kosher. Right? 1 times anything is the same, but it doesn't give us our units of measure. So let's take this equivalence and let's use another permitted mathematical manipulation. Divide both sides through by the same factor. So, and remember, we're dividing not the numbers, but also the units. So if we divide both sides through by 1 foot, I can do that, right? If you divide or multiply both sides of an equation by the same factor, you haven't changed it. So, but notice what this one is. 1 foot divided by 1 foot, 1 divided by 1 is 1. Okay? So if this is equal to 1, I can substitute this value right there. Okay, that's what I'm going to do. I'll take this out, and I'm going to substitute the equivalence of 1. Now, when we multiply that times that, remember, anytime you write a number or a unit by itself, just sitting out there by itself, it is understood to be in the numerator. So you could say divided by 1. So that means if this is in the numerator and that's in the denominator, that unit cancels and leaves us with this unit. So now that you've analyzed the dimensions or the units of measure, all we have to do now is multiply 6.8 times 12. All right, let's see if I've got that done already. There it is, 82 inches. And then check yourself, right? 2 significant figures. Those are exact numbers. 2 significant figures. And does that look reasonable? Well, if we multiply it by 10, it'd be 68. So 12 is a little bit bigger. Yeah, this seems reasonable. This is an example where you have, I'm going to have to speed it up. This is an example where you have a starting value that you want to change into a different unit of measure, but you don't have a single conversion factor. So what we do is a chained conversion. By the way, every conversion factor works because that conversion factor is equal to 1. And because it's equal to 1, if you need it flipped, you can do it. Like say 12 inches equals 1 per 1 foot, or 1 foot per 12 inches. Same difference. It's still 1. Okay, in this case, I'm going to let the animation do it for me. 4.5 pounds. We can convert pounds into kilograms, right? With this conversion factor. And then we can convert kilograms into grams, which is the value we want. So now that we've confirmed that all of the units cancel that we don't want and leaves us with the one that we do want, then we can do the math. So we say 4.5 times 1,000 divided by 2.2046 divided by 1. So there it is in scientific notation. These are exact numbers. So 3 significant figures here, 3 significant figures there. Okay, this is an extension of problem solving, right? And I chose this problem because if you've done any traveling, then you've probably already done this calculation. You want to know if you're going to travel from one location to another, in this case, example, New York to Los Angeles, you need to know some things to determine how much money you need to carry with you or have in your bank account so that you can charge the fuel to get you where you're going and then get you back, right? So this is a problem in asking yourself, what information do I have? What do I need to get where I'm going, right? So if we know the distance between Los Angeles and New York is about 2,500 miles, there's no conversion factor that will convert 2,500 miles into dollars. But we do know that we can convert miles into gallons of gas using the average mileage for our car. And then we can convert the miles, the gallons of gas into dollars by using this equivalence and this conversion factor. So there you cancel the miles. Oops, it didn't do that. I'm sorry, it didn't animate it. Cancel the miles, cancel the gallons. Now you have dollars. So under these circumstances, it takes $325 to get to Los Angeles from New York. And then it'll take that much to get back. And then if you're going to drive around some, you want to pad your expense with a little bit, maybe 15 or 20%. And that's how much money you need to have available just for traveling. Temperature. All right. There are 3 dominant temperature systems used in common use and in scientific use. Fahrenheit is used by weathermen, in the US at least. Maybe in other countries they'll use Celsius, but in this country we use Fahrenheit. And Celsius, of course, is another system, and Kelvin is derived from Celsius. So that's a fairly easy jump. We'll get to it. All right, Fahrenheit, and these are all named after people, last names of people. So Herr Fahrenheit was working in the biological sciences, and he wanted a system where he could measure temperature of living systems. So he chose 100 degrees as the average, say, mammalian temperature. As it turns out, humans are 98.6 and dogs and cats are about at 102.5. So he was roughly average. So he settled on a position in his thermometer that would give him roughly that place and marked it 100. And then he went to the coldest temperature he could produce, distilled water and ice made from distilled water in equilibrium will produce 0 degrees. Excuse me. No, it won't. It'll produce 0 Celsius. My mistake. Salt water. Right. He made salt water in ice. So it's like an ice cream freezer. Can get down to 0 degrees Fahrenheit. And then he marked it off and subdivided into hundreds. Celsius came a little bit later, but he wanted a system that chemists could use. And that means you need a way to calibrate your thermometers easily in any lab. So he chose 0 degrees as the freezing point of distilled water and 100 degrees as the boiling point of distilled water at 1 atmosphere pressure at sea level. And he marked his off. Now, when you measure the temperature of something, the amount of energy that's being supplied by the object is the same, no matter which system you use. So you measure the temperature at the freezing point of water is 0 degrees in Celsius, it's 32 degrees in Fahrenheit. You're measuring the same phenomenon. So they can be made equivalent. Kelvin, on the other hand, Lord Kelvin, by the way, wanted a system of temperature that was not subject to negative values, because in many of the calculations he wanted to perform, negative values would not survive the calculation. They were not permissible. So instead of having negative values, Kelvin moved his 0 point down to absolute 0. Nothing colder than that. And equated it to Celsius using the exact same size degrees as Celsius. So all you had to do is shift the 0 point. And now minus 273 in Celsius is 0 K. That means 0 Celsius is 273 K. So in order to find K, if you have Celsius, you add 273 to that value. That's the easy conversion. If you want to convert Fahrenheit and Celsius, you need a more complicated equation, because not only does the 0 point move, but the size of the degrees are different. Let's see. Okay, I didn't get anybody. I've already marked you guys. Okay. So for Fahrenheit to Celsius, Fahrenheit temperature is equal to 5/9 Celsius plus 32. Or your book might convert that fraction to a decimal, which will be 1.8. But that's an exact number, so it doesn't matter. Okay. So now that we have those conversions, we can convert any temperature between these two. If you need to go to Kelvin from Fahrenheit, you need to convert to Celsius first and then to Kelvin. Right? And those are your formulas. And this is an explanation for how that formula was derived. Right? We don't have time for it here. In fact, I'm running out of time. 12:55. Yeah, I've only got 5 minutes left. So if you convert the normal body temperature of a dog to Kelvin, first thing you have to do is convert Fahrenheit to centigrade or Celsius, and then Celsius to Kelvin. Right? So there you go to Celsius, and then you add 273, and you get Kelvin. Remember how to convert to Kelvin, because we're going to need that when we talk about some calculations, particularly gas laws. Now this one, I'm going to have to be quick with this one. There is a point where the value of degrees Celsius equals the value of degrees Fahrenheit. And in order to do that calculation, all you need is a little algebra. So you substitute X in for the temperature at degrees Celsius and Fahrenheit because they're the same. So it's the same variable, X, right? Once you do that and you solve the equation for X, you find that the value is minus 40. So minus 40 degrees Celsius is minus 40 degrees Fahrenheit. And I got a story that goes with that, but I don't have time to tell you. Okay. The mass of a substance per unit volume is known as density. Typically, the units of solid density is grams per cubic centimeter, and liquids are measured in grams per milliliter. The numbers are exactly the same because centimeters cubed and milliliters are the same volume. But the formula is D equals mass divided by volume. Now, any algebraic expression like that, if you know two of those variables, if you know density and you know volume, you can calculate mass. All you need is one unknown in a formula and you can solve for it. But the question arises, mass is easy, right? Just put it on a balance, measure the mass. But how about volume? Well, if it's a regular shape, there are formulas that will allow you to make a measurement and calculate the volume of that object. Regular spheres, cylinders, cubes, various things. But if your object is irregular, then when we do lab number 3, we're going to need to measure the volume of an irregularly shaped object. So we submerge it in water and we measure the difference from here to here. The displacement volume is the volume of the object. So you have a final volume and initial volume, subtract the smaller one, you get your displacement volume, and then you can calculate the density of this person. All right. Okay. So if we have a mass of 17.8 grams and 2.35 cubic centimeters, what's the density of the material? Just substitute the values and there it is. But notice you keep the units because none of the units canceled. We have grams, cubic centimeters. You must retain them. This is a situation where we know the density and the volume. We want to calculate the mass of this liquid. Right? So there's our unknown mass, and we solve for it. And it turns out that the mass should be 42 grams. Right? 2 significant figures here, 3 there, so we're going to limit it to 2. Now this one is a little more complicated. You have the mass of an object, and it occupies a volume of 1.125 liters. What's the density in grams per cubic centimeter? In this case, we have to calculate what is the volume in cubic centimeters. Right? So we need to do a conversion from liters to cubic centimeters. Then we can do the density calculation. There we go. Notice also that the density of this object is 1.95 grams per cubic centimeter. So the question is, will it sink or float in water? What's the density of water? It's about 1 gram per centimeter, cubic centimeter. So this object is denser than water, it's going to sink. Okay. In this case, we're saying, all right, if we know the density, we know the mass, we know the volume of water before we submerge the copper, what's the final reading going to be? We're looking for volume. So we can calculate the volume of the object using this formula. The volume of the object is 8.37 cubic centimeters. So what's the final volume of the water going to read? Well, we're going to add 8.37 milliliters to 50 milliliters. So add them together. And the water volume should be 58.4 milliliters after we submerge the copper. All right, these are final questions, and I'm right at 12:55. So we'll make it quick. This problem is a problem in what we call dimensional analysis. That's what we've been doing with unit conversions. Okay, so if we say an individual took 300 milligrams of trazodone, which is a lot, and it will put you to sleep. It's kind of a tranquilizer. Each evening before bedtime for 1 year, how many pounds of trazodone would he or she consume? And it tells us 454 grams in a pound. Well, we know what we're starting with, and we know how long it lasts for a year, right? Every day for a year is 300 times 365. So our starting point is 300 milligrams times 365 days. That equals so many milligrams. Oops. Okay. So it gives us so many milligrams of trazodone. Now we have that many milligrams of trazodone. We need to convert that to what? Pounds. So we convert milligrams, right, in the denominator to grams. This is 1,000 milligrams in a gram. And then we convert the grams to pounds because we are given a conversion factor. Oops, I did that backwards, sorry. Okay, 1 pound. So milligrams cancel, grams cancel, leaves us with pounds, and that gives us our answer. And check yourself, the answer should be 0.241 pounds. We're given a pound of feathers and a pound of lead. The density of each would be different, right? A pound, we know a pound of feathers and feathers have a lower density than lead, right? So it would be different. It's either C or D. And then, because why? Because it takes a greater volume. They would have different volumes. It takes a greater volume of feathers to make a pound, right? So they have different volumes. All right, that's it. All right, so next week when we meet, bring your safety document, print it off or put it in your Adobe Acrobat reader and fill in the values. And then I guess you'll have to print it off, but you can print it off then after you put in all the information, or you can write it by hand. I don't care. And then you're going to give me your safety contract and the quiz. Right? That's what you'll hand me next Friday, assuming that it's not snowing again. And then we will we'll talk about chapters 3. Oh, yeah, I mentioned the review when we went into Brightspace, and we saw all those PDF files of reviews for chapters 1 through 3. You can print those off, or you can look at them and work some of the problems yourself. And then when I get there next Friday, I'll give you a hard copy. And in fact, I think I have a key that goes with it. So get started working some of those problems, because the more problems you work, the better you'll get at it. It's a skill. And I'll just part with one last word. Your two best friends in chemistry are curiosity. You always want to know more. You want to know why something happens. You want to know how it happens. You want to develop a skill that allows you to investigate things. Curiosity and boredom. If you work these problems and you work so many of them that you're bored working certain types of problems, then you probably know them pretty well. So that's a good indicator that you're well on your way to mastering the topic. Okay, that's it.